Let me, I'll be trying to walk about a bit. I hope that's okay. Let me start by saying thanks to the organisers for inviting me to participate in this summer school and memorial conference for Pierre Barres. I really do appreciate being included in this actually quite intimate group, but thank you really. Tomorrow at the conference, I shall say a few words of my own memories of Pierre, and also of János Urai, a famous colleague of ours, many of you will know, who very sadly was killed in a climbing accident just 2 weeks ago. So that's tomorrow. Today I'm going to try and focus my attention on the early career scientists amongst you here. And I hope we can have a little discussion along the way. My presentation will be probably quite chaotic, so feel free to jump in and ask questions. I'll be very happy to clarify things. I'm going to talk about the mechanisms of deformation and healing that occur in rock salt and in crushed rock salt materials used in sealing applications, putting a lot of emphasis on the role of water. Okay, and these deformation and healing processes are really what makes rock salt such a wonderful sealing material, such a remarkable sealing material, and is responsible for the many applications that it has to offer as a geological resource. So let's see if I change the slide here. Okay, so this is rock salt. Any of you that might be working on modeling rock salt and have never seen a piece of rock salt, then you should be ashamed of yourself. There's always a couple in there somewhere. Have a look at this material. It is the most beautiful material you can imagine. At least it's one of the most beautiful materials I can imagine. Here it's this lovely crystalline, dense material. If you make an optical thin section, you will see the dense crystalline structure. Grain sizes typically around 5 millimeters. Natural rock salt, anything between a few millimeters and perhaps a few centimeters. It has an exceedingly low porosity, mostly disconnected, of the order of 1%, and very low permeability. Typically, in the undisturbed condition, maybe 10 to the minus 21 or 22 meters squared. Very low permeability. Why is that? That's because it is so extremely ductile. And it has such a low resistance to creep. That means that rock salt deposits which are buried, even 100 meters, they will densify and compact very rapidly into this impermeable dense material. Okay? So as well as this high ductility and low creep resistance, of course it's highly soluble, which means that any cracks that open or whatever can be sealed by dissolution reprecipitation process. So these are all very important aspects of its basic properties and its importance. If you think about the ductility and the low creep resistance, it's wonderful to actually observe that firsthand. Here you see single crystal of sodium chloride compressed in the 100 crystallographic direction in a very simple unconfined compression test, and you see it's perfectly ductile at room temperature at really rapid strain rates. If you cleave a crystal of sodium chloride, a long stick, which this was, a long stick-like cleaved crystal of sodium chloride, and you hold it in your fingers, and you put it in a solution of sodium chloride that is undersaturated, and you wash it around, you can deform it with your fingers without it breaking. And these are my fingers doing just that. Okay? You can deform it plastically in your hand without any problem at all. And of course, this plastic deformation is intracrystalline plastic flow. It's caused by the motion of dislocations, dislocation loops, with edge dislocation and screw dislocation components glide on the, in particular, the 110 1 bar 1 plane. This is the 110 plane in the 1 bar 10 direction. Here you see the slip traces formed on the surface of that crystal. Okay, so it deforms by intracrystalline plasticities. It's an amazing material. Yesterday, Christian mentioned the brittle ductile transition. So the brittle to truly plastic transition in sodium chloride with rock salt occurs at a couple of 100 meters depth. Okay, so it's an extraordinarily ductile material, and why is that? So I'm just going to ask you guys, are you early career researchers, PhD students, maybe some postdocs amongst you, why is that? Come on, let's have a bit of interaction. Why is that? Why is this so different from something like a sandstone? There's a very fundamental high school reason for this. Why is it? Why do you think? Come on, have a guess. No, there's no sign of intelligent life on this planet.
Crystalline imperfection?
Yes, but quartz also has crystalline imperfections. But give me more, come on. Why is that? You're thinking along the right lines. The reason is, excuse me, because it's ionic, okay? And quartz is a covalently bonded mineral. So because it's ionic, the bonds are weak, all right? So the bonds are weak, that means it's easy to move dislocations. It's easy for ions to jump out of the crystal into solutions. Dissolves easily, okay? So the activation energy to break bonds is very low compared with crystalline materials like silicates. Right? Carbonate calcite is also ionic, and the brittle ductile transition in calcite occurs at about 5 kilometers depth, okay, or a little less, maybe 3 at the height of the gradients. Because these are ionic materials, they have weak bonds, they dissolve easily and dislocation moves easily, bonds are weak. Right. So that's a little bit of really basic stuff, but it's kind of nice to be aware of it. Now, these properties of rock salt make it really very, very useful. So it's an extremely important, my pointer is just about, is it visible? Okay, so starting with the top bullet, of course, it can be mined by solution mining very easily. It's a very important source of sodium chloride for the chemicals industry, let alone table salt. Here you see a map of the Netherlands with the main regions where we have salt, Permian salt, Triassic salt, vast deposits. Many countries have such salt deposits, of course, Germany, here in France, right across Central Europe into Russia, the United States, China. Salt basins are common around the world. So it's an important resource in many, many countries, not just for mining as a supply of sodium and chlorine, but for creating storage caverns for oil and gas, being used very widely for that purpose. And of course now it's very much in focus for renewable energy storage, storing hydrogen or storing compressed. Okay, it's very, very long been in the picture for radioactive waste disposal or storage, and of course its very low permeability and porosity means that it's a fantastic trap for hydrocarbons, and very many of the hydrocarbon deposits around the world are actually trapped under rock salt or around rock salt structures. And then, you need to know about things about how salt flows because of things like wellbore solutions. All right? Now, in the Netherlands, we have some of the deepest and largest salt caverns in the world. They're not really astonishing, some at 3 kilometers depth. And you can easily pop the Eiffel Tower into several of these, and there are also several up here where the world's tallest building, that's the Burj Khalifa, I probably pronounced it completely wrongly, but I'm sure you know the one I mean, the one in Dubai. It's 800 meters, 820 meters tall. You can put that inside several of the biggest salt caverns in the world. So it's important, and the focus now on hydrogen storage in particular is really, really very, very much driving a lot of new research. So let's consider a few of these sort of applications. What are the effects of these activities? Of course, anything you do in the subsurface is going to create some impact, and there are questions about what will the performance of these systems be, what will the integrity of these systems be. If we think about creating solution mine cavities, then there are a couple of geomechanical or environmental challenges we have to think about, right? Of course, removing salt from a salt bay or a salt dome will lead to subsidence. Solution mining will produce subsidence at the surface as convergence creep. Ductile flow, the salt that will converge into the cavern, very often it's used as a means of simply exploiting the salt. You mine the salt out by dissolving it, and it creeps in to the region that you're dissolving, and that's how you produce the salt, and it of course produces subsidence at the surface. When you have to close the facility, you're probably going to have to shut in the brine, and then there'll be all sorts of flow in the surroundings as stress adjusts itself and deformation redistributes itself over a larger region. Okay, so there will be some evolution in this subsidence in the long term, which in a country like the Netherlands is very, very important because we're already below sea level, right? So, if you have this going, right, you're in deep trouble. So this is especially important in the Netherlands, but it's also important in other countries as well, of course. Now, talking about abandoning such a cavern, closing it in after you finished using it, it doesn't matter if it was made for salt mining or if you were going to be, perhaps you've made a hydrogen storage cavern, and at some point in the future you're going to abandon it. It's not going to be there forever, right? So how are you going to do that in the cheapest way? That's what the companies will be thinking. And we're going to fill it with brine and shut it in. Well, how is that going to evolve in the future? And that salt is going to creep in on that shut-in brine. The pressure in the brine is going to go up, okay? And at some point it'll become, at the top of the cavern, it'll become roughly equal to the local lithostatic pressure. What happens then? Does it fracture the roof and come out? Does it permeate somehow into some damage zone around the salt? Does it do some sort of combination of those things, some sort of shear zone which becomes permeable? What will happen? This has not been really considered very carefully. So there's some important questions here for long-term stuff, which is way, way longer than the timescale of experiments, okay? Right? So, extrapolating lab data is going to be filled with uncertainties. And what are the public going to ask when these things have to happen? They're going to say, what is the uncertainty? We better be sure that we can tell them. Now, let's think about hydrogen storage for a second. It's of course a special thing, really. So I'm starting out here so you can see my pointer. If we talk about hydrogen storage, this is going to be cyclic, okay? When energy is available, you put in hydrogen. When you need it, you extract the hydrogen, so you have cyclic loading of the system. Hydrogen is a small molecule, so one has to think about whether it can penetrate into a damage zone, which will always exist at the margin of the surface of such a cavern, okay? Where the mean stress is relatively low. What will be the effect of pressure cycling? What's the effect of frequency of cycling? what's the extent of any permeable zone that develops here, what will the stability and integrity of such a system be, especially if you've got layers of other stuff, and so on. Okay? And very important thing, which I know several of you are working on here, hydrogen pressure is going up and down. Solubility of water in hydrogen is dependent on pressure and temperatures. Temperature, pressure changing, thermodynamics of the gas, okay? Compression. Water is going to be precipitated, evaporated. How is all that going to affect this damage zone, what happens? So let's think about that in a bit more detail. This is sort of hypothetical, and let's hope it won't be a problem, but we don't really know. Okay, here's the cavern, and it doesn't really matter too much at the moment if we're thinking about whether this is a producing cavern or an operating cavern or a cavern which has been shut in and sealed. There will be convergence of the salt, right? Convergence of the salt, pressurizing the fluid towards the cavern. And that will mean that there's dilatant deformation of the cavern wall. That will tend to increase the permeability of the rock salt. Fluid will be able to go in, whether it's gas, brine, or gas with water dissolved in it. It will move into this zone. There'll be some sort of interaction with the fluid. So the salt-soluble changes in humidity will absolutely definitely affect it. How will that influence? There will be fluid-assisted deformation processes, but there'll also be healing processes. How will they compete? How will that influence the ongoing deformation? Could there be positive feedback loops here which are undesirable, or will there be negative feedback loops which will stabilize the whole thing? These are important questions that we need to think about. For radioactive waste disposal in salt is essentially the same kind of thing. If you imagine putting some high-level waste or low-level waste inside a salt structure, then you want to seal the route between that and the biosphere, the hydrosphere. That means filling up voids, cavities with things like crushed salt, right? And then you can imagine, okay, you've filled a gallery with crushed salt, and the rock is going to converge by critical, that ductile flow is going on there, and it's converging on the cavity, compacting this backfill. There might be some in boreholes as well. Crushed salt. How long does it take for that to become impermeable? And these are all extremely important questions. Okay? Right. So what do we need to model the performance of all these different kinds of systems? Of course, we need crate laws to describe the flow of the salt, the convergence of the salt. And I'm sure Laura is going to say much more about transient creep and the incredible complexity of the effect of boundary conditions and different loading geometries. I'm only going to talk today about steady state, okay? And you can address a lot of problems of the first order of steady state creep. I think Laura's having a little laugh at me because people are absolute nonsense. That's fine. But to a first order, many of the questions can be addressed looking at steady state flow properties of rock salt. And I'm going to tell you something about the mechanisms, because at least we know something about that for steady state case. It's much more complex for transient. So as well as creep laws, we also need laws that describe damage development, permeability development, and healing. Okay? We need constitutive equations that describe these things. And it's, in my opinion, very important that we understand the microphysical basis behind such constitutive law. Okay? Because if we don't know the processes, we can't be sure that we've taken things into account properly. We have no basis to extrapolate from laboratory data to the longer term. You need a physical basis. And that's where material science comes in, and that's sort of where I come in. I'm not an engineer, but I've spent my life working on the material science of rock. Okay? So, I'm going to tell you about the material science of salt, and I have no idea what your backgrounds are, so if something is weird or strange, you just ask, okay? And if I don't finish, if I don't get to the point I plan to get to, well, never mind, we'll continue over that. So let's start with creep mechanisms in dry rock. I say dry here kind of loosely, because sadly, only relatively recently have people realized the importance of humidity or moisture content in influencing the properties of rock salt. So it's very, very often been assumed to be dry because the water content is so small. And it's very, very often been assumed that water simply can't fit rock salt. So I recall in 1982 going to a conference, Pierre was there, and some colleagues from another country said to me, you can't possibly dry the water, you can't possibly affect salt because it's a saturated solution, nothing can happen. But a saturated solution of salt, but that may seem to be the case to an engineer who's never studied any chemistry, and I understand. But the solubility of the material is dependent on the reference state. So dependent on solubility for solid. In what state is that solid? If you change the thermodynamic state of the solid, you change the solubility. Okay? So it was very often assumed that rock salt can be treated as dry salt and it's all fine and every salt sample will be exactly the same. So despite that massive oversimplification, Darrell Munson and Dawson in the early 80s drew this deformation mechanism map for steady state flow of rock salt, okay? Which was replotted by Pierre et al. In 2019 to make in what I feel is a much nicer diagram. But this type of map, if you're not familiar with the deformation mechanism map, it shows the log of deviatoric stress normalized with respect to shear modulus. Okay, so this is the flow stress, if you like, against temperature. This is homologous temperature measured in terms of the ratio of the absolute temperature to the melting temperature in Kelvin. Okay, so this is the melting point. Here you see the temperature in Celsius, melts at about 804 degrees. And this is the deviatoric stress in MPa here, so this would be 1 MPa, 10 MPa. These different fields show the range of conditions, the range of stresses and temperatures at which particular mechanisms dominate flow. Now this map was drawn assuming a grain size of 3 millimeters, which is important for these solid state diffusion processes here, which are grain size dependent. They're so slow, Cobra Creek and the Barrow Herring Creek, this is vacancy controlled solid state diffusion. These are so slow that they will absolutely not be important under subsurface conditions that we're interested in. Okay, so this range of conditions is what's important for the subsurface. So from stresses below about 20 MPa and in a very narrow range of temperature from 0 to perhaps 120, maybe 200 degrees at the most. This is a range accessible in laboratory conditions. Okay, so that means that if you're having to describe what's happening down here somewhere, then you've got to extrapolate many orders. Now, these fields here, this is where dislocation, motion, controls deformation, and this deformation map actually it is really pretty good considering how long ago it was drawn. It was drawn on the basis of very fundamental data on the crystal structure properties of rocks. So this already tells one, told the community, all those years ago, you'd expect dislocation glide and dislocation climb to be important deformation mechanisms in the lab. But it was recognized then that it was not known what happens down here. We don't know, or we didn't know at that time. And I'm going to show you today that now we do know what that is. And there's still some controversy about it, but at least I think we know what it is. Right, so let's go to something a bit more schematic. Imagine doing a triaxial test on rock salt, okay? So we're going to do conventional triaxial compression test at elevated confining pressure, and we're going to measure the creep behaviors, we're strain against time, and this is typically what you see if the confining pressure is high enough to suppress any tendency for micro, okay? So you'll see primary creep and then some steady state creep after some time, could be quite long. This is, during this period, this is where dislocations are being multiplied in the material, and at some point, a variety of different processes lead to the annihilation of dislocation. So here you have dislocation multiplication, and then they start to interact with each other and annihilate until you get a steady state population that controls the creep behavior. That's in dry salt. If you reduce the confining pressure, or maybe do an unconfined test at sufficiently high deviatoric stress, then you see the same sort of behavior qualitatively, but ultimately you'll start to get some acceleration in creep due to damage development. Okay? And of course, this all depends on the deviatoric stress and the mean stresses. Okay? So we're going to focus right now on what happens under conditions where we do not have dilatancy, or at least where people thought we didn't have dilatancy. This is where the individual crystalline grains in the rock are deforming by dislocation motion. Okay? All right. So this is just a plot showing an arbitrary collection of data on steady state creep of salt at this temperature, 70 to 80 degrees. It's a plot of the log of the deviatoric stress, the log of the flow stress against the log of the strain rate with minus 12, here, so it's 10 to the minus 12 per second strain rate there, increasing up here to 10 to the minus 2. Okay, now here you see different sets of data with a few lines kind of fitted, 10 MPa here, 1 MPa here. So most of these kind of data, it's been known for 50 years that they fit this type of power law equation, okay, where the steady state creep rate is related to the flow stress, the deviatoric stress raised to a power n, which is typically about 5, and there is an Arrhenius temperature dependence of the creep rate, okay? And any particular set of data can be fitted quite well to that type of flow law at stresses between about 5 and about 15 MPa typically. Okay? It almost always gives you a pretty good fit. Sometimes the n value is lower, sometimes it's higher, but you can almost always get a reasonably good description of creep data on salt at those stresses with the power law. So this can be regarded as a dislocation creep law, if you like, an empirical one. And there are many such empirical descriptions of the flow of rock salt which have been created for many different salts. And everyone is slightly different, and we'll see a bit more about that in a second. But of course, there's a big issue here. Well, you know, how do you know if you can extrapolate that? So, what are the processes actually going on here that control this behavior? So first I'm going to talk about something that we call climb-controlled dislocation creep. If edge dislocations, this is an edge dislocation, if the motion of edge dislocations is what controls creep, then there are a number of things that play a role here. This diagram here, this is purely schematic, okay? the motion of the symbol is a symbol for dislocations, edge dislocations. The motion of edge dislocations through the crystal structure, along a glide plane, can be resisted by the glide motion itself, by the breaking of bonds in individual steps, okay, as the dislocation glides through the structure. And it can also be influenced by obstacles. So this is an obstacle, okay? There are many, many different kinds of obstacles to dislocation motion on different scales. Typically, some either repulsive or attractive interaction with dislocations on neighboring glide planes will impede dislocation motion, and the rate of dislocation motion will be controlled by the rate at which these obstacles can be overcome. One important process, which is known in many, many materials, is which allows edge dislocations to overcome such obstacles, is the process of dislocation climb. Dislocation climb simply means that the dislocation moves up by one atomic spacing when a vacancy, a missing atom or ion in the lattice, diffuses to the tip of the dislocation, the core of the dislocation. That produces this climb step. And this is one way that dislocations can move out of their glide plane and overcome obstacles, typically annihilating. They migrate and they will be attracted to dislocations of the opposite sign, the opposite orientation of the half plane coming up to, and they will annihilate. And you will get a steady state flow behavior, which is competition between multiplication and this annihilation of dislocations as they overcome these obstacles. Okay? Now, there are many different models at the microdynamical scale for this. They all kind of look like this at the end of the day. This is the predicted steady state strain rate. Here you have the flow stress normalized with respect to shear modulus raised to the power n. And this is an Arrhenius temperature dependent term, right? This is an activation energy here, yeah? And Boltzmann's constant and temperature. So, of the vast range of microdynamical dislocation models for this type of process, you typically get an n value somewhere in the range 3 to 5. And an interesting point here, which I'm going to sort of pull up a little bit of information which is very rarely presented in solid mechanics. This activation energy in principle should be pressure dependent, because when a vacancy moves through the crystal lattice, there's a time dilation of the crystal lattice, okay? A very, very tiny dilation of the crystal lattice. So that if you have a high pressure, work has to be done to move the vacancy. So work has to be done to climb the dislocation. So the strength becomes pressure, okay? So this essentially now, if you look at this, a strain rate, the stress raised to the power n, and Arrhenius temperature dependence, which has got a pressure dependent term in it, that looks very much like this type of fit that I just showed you in the slide before. So actually, in broad terms, this type of model for the microdynamical behavior of dislocation motion predicts behavior which is pretty similar to what you see in rock salt and many instances. Okay. On the other hand, screw dislocations, which have got a much more complex geometry, they could control the motion and the deformation of the material. So, in the case of screw dislocations, the story is basically the same, except they can only get out of their glide plane, they can only overcome obstacles by slipping into a different plane. Okay? They cannot climb. If a vacancy arrives at a screw dislocation, it does nothing to allow it to move out of its glide plane. They can only slip into a different cross-cutting plane with the same slip direction. And this is a much smaller scale process. It's an atomic scale jump process. And microdynamical models of this predict a strain rate which is proportional to this stress squared term here, but then exponentially related to an activation energy which is very strongly dependent on stress and also dependent on pressure. Okay? Now, again, there are many models for this, but basically, if you have cross-slip of these screw dislocations controlling what goes on, this predicts that the material becomes weaker at higher pressure. And our last one predicts that it becomes stronger with increasing pressure. Okay? So, creep rate should be accelerated with increasing pressure if the cross-slip is controlling. With screw or edge dislocations, you have glide motion as well, and in principle that can control the rate of deformation. In principle it's possible, and if you look at it, if you make a microdynamical model for dislocation glide, you get something which also looks very much like this. For screw dislocations, also for edge dislocations, right? And but the effect of pressure is almost nothing. So if you have glide of dislocations, just gliding through the lattice, if that's controlling deformation, there's no effect of pressure. If cross-slip controls the rate of dislocation motion, then increasing pressure makes the material weaker. If you have climb controlling deformation, increasing pressure makes the material stronger. It will cause a deceleration of creep. Right, now that gives us a way of actually trying to figure out what processes are important. So, very, very, very quickly look at some data just to let you see how incredibly variable it is. So here's some early data from constant strain rate experiments Hugh Hurd in 1972. This is log stress plotted against minus log strain rate. So this power law type of behavior would appear here as a straight line, right? A log strain rate would be log A and then minus Q over RT n log sigma. So you see that if you plot log strain rate, log stress against minus log strain rate, the slope of this is 1 over n, right? So from the slope you can get n, and what Hurd found in this region, so at stress is below 10 or 15 MPa, n is 5.5, the activation energy close to 100 kilojoules per mole. Okay? And up here you see that that power law doesn't really fit anymore. An exponential law or a hyperbolic sine law would fit a lot better at higher stress, suggesting a different mechanism. This is data from Carter et al. 1993. Log stress against minus log strain rate again. You see data at different temperatures again. And it's a little harder to see what's going on here, but basically this data was fitted with the power law, and at lower stresses, N was about 3.4, and the activation energy quite low, 50 kilojoules per mole. Then you see this data tends to swing over here. N goes up to 5.3 and the activation energy goes up. So actually you see the same trend here. There's some increase in the strain rate sensitivity of stress as you go to higher stresses. This is some data at Hunscher and Hampel. It's the log of the normalized creep rate against log deviatoric stress, normalized with respect to shear modulus. Basically, this plot shows the strain rate divided by e to the minus q over RT or KT, okay? That simply is a way of correcting the strain rate for the effect of temperature. So all the data for different temperatures fall on the same line, and that fit gave N as 7 and an activation energy of 110 kilojoules. Here's some more data. Same sort of thing, log flow stress against log strain rate, power law fit, N is 5.6, and activation energy 80 kilojoules per mole. So you see there's a lot of variability, okay? And now we're going to just compare these things at 125 degrees. This is log flow stress against log strain rate again. And what you see here now, these power law fits from a whole bunch of different studies. And at any particular strain rate, you see here, look, this is log stress of 1, 1.4, 1.5. There's about a half an order of magnitude variation in strength in the flow stress at a fixed strain rate. And at a fixed flow stress, there's 2.5 orders of magnitude difference in strain rate. Okay? So you can see there's in fact tremendous variability between all these different experiments on salt. I think, well, it's NaCl, you know, they should all be the same. Well, they're not. There's a huge variation. So if you were to kind of take a flow law from here and apply to a different salt, you could easily be 2.5 orders of magnitude out in strain rate. Right. So let's see what can we say now, making some bit of a summary of that. Of the steady state data at 20 to 200 degrees and differential stress, the toric stresses in this range 4 to 15 MPa. Creep is well described by power law, generally speaking. Okay, steady state creep is reasonably well described by power law. N is often around 5. The activation energy is often in the range 50 to 100 kilojoules per mole. Okay? That suggests that it might be climate controlled in that region because these microdynamical models of climate control predict something like that. Okay? At higher differential stresses, 15 to 20 MPa, many of those data I showed a swing around to a higher sensitivity of the strain rate to the stress. Okay, so if you like an increase in N value, that implies an exponential creep law would fit better, or even a hyperbolic sine, a regularized exponential creep law would fit better. That would be more consistent with dissipation collide. So it does suggest, mechanical data itself suggests some transition with increasing the toric stress from climb control to glide control. Why is there so much variability? This is really kind of shocking from the point of view of a material scientist. So I'm going to appeal to you engineers amongst you. I know you're not all engineers, but some of you are. So I'm going to appeal to you now to please think about the structure and properties of the material that you're testing. It doesn't just exist. Why is there so much variability? Well, one reason is because solid solution impurities in salt, the differences in ionic impurities, affect atomic scale processes like the motion of dislocations. Okay? So you would expect quite a lot of variability just due to the chemical composition of the salt, even with very small changes in chemistry. Fair enough, but at least one can relate it to that. If you analyze the stuff, you can actually see what sort of trends are present. What is really important is that some samples were indeed tested dry, but some were unconfined and some were allowed to dilate, whereas others were actually contained water, were tested confined, and did not dilate. So there's all sorts of other stuff going on here. If water is present, you'll see shortly, it has a really big effect. And people in the past never measured the water content of their samples, and they very rarely checked whether their samples' water content might have changed, or whether that might be related to microcracking and dilatancy going on in the sample. The water content very often unknown, and there's all kinds of other processes, for example, growth of new crystals during the deformation experiment, which amazingly, for more than 50 years, people mostly didn't look at, only in a very few studies. So, you know, characterizing the sample before and after an experiment is really, really important. So, what are, what do we see if we look at the samples? Okay, so at 20 to 200 degrees and at these different deviatoric stresses below 10 to 15 MPa, so this is where we have nice power law behavior, you see a microstructure like this. These are optical micrographs of cleaved chips of salt from the inside of a deformed sample. Okay? So, cleaved chips of sodium chloride from inside a deformed sample only tell you what's happening inside one crystal in the sample. They don't tell you the relationship between different crystals. Okay? It just tells you what's inside one crystal. Now, fair enough, what you see typically is these beautiful networks, which we call subgrains. They are arrays of dislocations, we call them walls of dislocations, and in material science, these are absolutely characteristic of dislocation climb. Dislocation climb is needed to form these structures. Okay, so at this range of stresses, below 10 to 15 MPa, in dry salt samples or nominally dry salt samples, most of the data I showed you is associated with microstructures that look like this, and these are, in this particular case, you see individual dislocations here that are made visible by etching the cleaved crystal of salt. And these are arrays of dislocations. This is a similar thing here. You could just see the free dislocations and these arrays of dislocations. It's evidence that dislocation climb was an important mechanism. If you go to the higher stresses where we saw the more exponential creep, I'm not sure if this is, okay, you see my red spot here, I come in here. The higher stresses, the microstructure really looks quite different. Okay, you see these elongate deformation bands and some blocky subgrains, these blocky cellular structures. This is what you see at higher stresses. Okay, and I want to emphasize here these particular samples, synthetic rock salt, deformed where the water content was extremely well characterized. So we know it's less than 5 ppm water, but it is really dry. Okay, then you see these are polished sections, and you see the relationship between the individual grains. And all that's happened during these experiments is the grains are flattened plastically by dislocation motion, and that dislocation motion is concentrated in these banded structures. This is evidence pointing more to dislocation glide or cross-slip dominating the microstructure. Okay, so that kind of fits in with what we see in the mechanical data. Now, there's an interesting little touch I want to add just because it was my idea. I talked about this pressure dependence of these mechanisms, right? Now, in our lab in Utrecht, we have facilities for doing deformation experiments on mantle materials, so we can go to very high pressures and temperatures. So we thought, well, why not do some really high pressure experiments on rock salt to actually see if we can discriminate a pressure effect. You know, does the strength increase with increasing pressure, or does it decrease with increasing pressure? And does that tell us if it's glide, cross-slip, or perhaps climb control? So here's some results. We did experiments up to 600 MPa, okay, so 6,000 bars. And these are stress strain curves at room temperature and a pretty rapid strain rate. And there's all sorts of complexity here. I just want to focus on the large strain behavior where it's still work hard and quite strongly, but ultimately it will develop some sort of steady state there. And what you see is, as steady state regime is approached, behavior at 600 MPa is very slightly stronger than at 50 MPa. So there's a a very small effect of pressure as a fraction of the total strength. At 250 degrees in the strain rate of 10 to the minus 4, so it's same strain, higher temperature, and at 50 MPa, you see beautiful steady state behavior. At 600 MPa, the sample is proportionally much stronger and still work hardly. So you see that there is a clear strengthening effect of pressure at the higher temperature, low stresses, right? Higher temperature, low stresses, there's a clear effect of pressure, and at low temperature and high stresses, there's very little effect. So this is also consistent with the transition from climate-controlled creep, which is predicted to be pressure dependent, and glide-controlled creep, which is predicted to be insensitive to pressure. Okay. Amazingly, the microstructure of the samples, regardless of the stress, if you actually look at these little subgrains, these little cell sizes, and you plot the log of the subgrain size against the log of the flow stress, the steady state flow stress, these little cellular structures that develop, their size is systematically related to the flow stress. And it's almost linear, not quite. So the size of these cells or subgrains is proportional to the stress raised to the minus 1.15. So it's almost inversely proportional. Okay? These cell structures get finer with the higher the stress. And this experimental data has been used by people like Janos Urai, who did this wonderful work. This is an irradiated sample of natural salt. If you irradiate natural salt with, for example, gamma rays, you precipitate sodium metal particles. They will precipitate on defects, and the extent of precipitation is influenced by desiccations and by other impurities. Okay? What you see here, the grains in the salt, and you see these subgrain structures, these cellular structures. The blue color is due to sodium precipitation. This is in a natural rock salt from the Netherlands, a bedded rock salt, and Janos measured the size of these grains, and the size fell down here, and that actually suggested that would be consistent with the flow stress in nature, okay, in this natural salt body, a flow stress between around about a half to a little less than 1 MPa. Okay, so you can use this kind of information to actually say what the flow stress was in a natural salt, or in an experimentally deformed salt. Okay, now, coming back to the data I showed you earlier. Log stress, log strain rate plot, power law description of typical experimental data in temperature range 70 to 80 degrees. But what I've basically told you now is fine. We have some understanding of the mechanisms that cause this type of behavior, probably time control, dislocation, creep at the lower stresses here, maybe glide control, may transition to glide control gradually towards higher stresses. But when you look at flow rates in natural salt, so from measurements of salt motion in the geological record, you look at things like rates of flow of salt glaciers, and so extrusive salt bodies that reach the surface. You look at closure rates in caverns on the very long term. There's very often evidence that deformation is occurring a bit too fast to be explained by this type of data. And imagine you're going to try to extrapolate this. Okay, it's going to be too slow to explain what we see in natural salt. So, in the American Gulf Coast, for example, salt is moving at strain rates of 10 to the minus 11 or something like that. And we know that from boreholes through it for oil and gas, which are getting sheared off. Okay? So these strain rates are like here. It's a bit hard to extrapolate that. So, what is actually going on at these low stresses? And the low stresses are going to be important for the long term, for that long-term subsidence above caverns, so that long-term lower stress behavior when the fluid becomes pressurized in the cavern and you have to think about the leakage of fluid, right? What's actually happening? Now, that last slide I showed you give you some clue actually. Now, these are subgrains. These are formed by climb control groups. There must be some climb control going on, dislocation climb is going on in natural salt flowing in nature, so at low rates, at stresses of, like half an MPa or something. So there's some dislocation creep, but perhaps that's not the whole story. And so what controls creep at low stress? I'm going to say much more about this in my conference talk tomorrow. So I kind of hope you'll all come to that, because I'm going to have to skip over it now and miss the details now, otherwise I have nothing left to talk about tomorrow. Okay? So let's look at some more naturally formed salt. This is from the Avery Island salt dome in the Gulf Coast of the United States. Right? And if we look inside, this is within an individual crystal. The grains are big, 5 millimeters typically. Looking within a single grain, this is an etch, a thin section of salt from the salt dome etched. And that etching process reveals this subgrain structure, which is so characteristic of climb. Okay? This is an irradiated, a gamma irradiated piece of salt, which has also been sectioned. And Janos, Ura, and I did a lot of work we started this type of procedure years ago, and Janos took it and developed it into a fine art, really. But this is a beautiful section of Avery Island salt, where you also see these cellular structures revealed by precipitation of sodium on these subgrains. But as well as that, you see clear evidence of overgrowth, zoning caused by crystal growth. Okay? So the subgrains suggest, yes, during natural flow of the salt, there was some dislocation climb, but there's clear evidence for overgrowth, suggesting dissolution and reprecipitation. Okay. Now we come to something really important, at least in my opinion. Grain boundaries in salt, they always contain water. They always contain water, unless you screwed up something and lost it all. Okay? So all natural salt contains grain boundary brine inclusions and films. So this is a section, you see these little fluid inclusions, they contain brine. I see a couple of you taking pictures. You can have this presentation afterwards, so don't worry about that. Okay? So you see all these inclusions in here, and if you look in there, you see there are little films of brine. We've measured it with infrared spectroscopy and so on. So amazingly, this is a natural salt, the Speisesalz from the acid mine in Germany. The grain size is quite coarse, okay, say 5 millimeters, 100 parts per million of water. If it resides at grain boundaries, and you have a grain size of 5 millimeters, that means you have a 300 nanometer film coating every grain. Okay, 300 nanometer film of water. For the water film people in physics and chemistry, that is a thick film. It has the properties of liquid water. All right? So you have a path here for, potentially you have a path, if these are connected, if these films are connected, you have a path for very rapid diffusion in the liquid phase instead of in the solid phase, which is 11 orders of magnitude lower. Right? So diffusion in the fluid films very fast. That should mean that a mechanism which geologists call pressure solution, that ought to be possible. Pressure solution is a process of diffusive transport driven by stress gradients. Okay, so diffusive transport around the grains driven by stress would of course lead to removal of material from high stress interfaces, deposition at low stress interfaces. That's a creep mechanism. It's a chemical process, it's a creep mechanism. Okay? So it should be possible, at least if one says, is there water present? Yes, water is present, so this type of process might be possible. And not only that type of process, so should transfer not only around the boundaries of the grains, but actually across the boundaries of the grains, between the crystals. If you have a crystal with lots and lots of dislocations, like this one, and a crystal with only a few dislocations, the stored energy is different. The dislocations distort the crystal net. It's full of stored energy. So these will be high energy grains. So if you like, you think about the level of vibration of the atoms and ions in those crystals, it's higher, okay, than in this crystal. So ions are going to jump into the fluid, diffuse across the boundary. So you get migration of the boundary, you get recrystallization. This should be possible. Is it there? Does this happen? Now, from 95% of the experiments done in the last 50 years, we don't know because people didn't look at the samples. It's simply true. The first time that it was seriously looked at was indeed by Janos Urai and myself and some colleagues at Utrecht University coming from the material science angle. We did experiments on natural salt and we looked at the microstructure and we did stress relaxation experiments. So we deformed the samples. These were at 150 degrees and samples which were tested under confinement pressure, 10 MPa or above, they showed a transition from high N value creep behavior to N is 1 creep behavior, which is a characteristic of this diffusion transport process. Okay? So this behavior is absolutely totally different from the N is 5 type behavior. What we found was that if we did the experiment at low pressure, low confinement, the sample dilated, we measured a volume change, a very small volume change, we measured a volume change, but at 150 degrees, if the grain boundaries migrate, the course of water immediately goes into the vapor phase and will no longer be capable of supporting this process. And so we did not see this transition to behavior with N1. When we looked at the microstructure of the sample, we saw this amazing transformation that the original material was highly deformed. Here you see all these dislocation boundaries. This is a grain boundary in the original material. You see these this cellular and banded structure. Those are dislocation structures somewhere in the boundary between climb and glide control. And we saw these incredible new crystals growing, and they contained brine, they contained water in the boundary. And this micrograph was taken by Janos. He became a real specialist in this, and it completely changed the microstructure, changed the grain size, and that's what it caused a transition to this pressure solution mechanism. Now, a little bit about the theory of this. So, may I ask, Alexander, when can I stop? I assume I've got an hour and a half since we started.
Yes.
Is that okay? Okay,
Okay,
so you tell me when I have to stop, okay? And don't be shy. All right.
25 minutes.
Okay. So let's think a little bit about this mechanism. It's some of you may know all about this. It may be new to others. So this is a grain in a dense rock salt or a dense rock material. It's perfectly general. It occurs in many other materials as well. Let's say the grain size, the diameter of these is D, all right? And we apply a deviatoric stress, let's say sigma 1 in this direction, sigma 3 in this direction, and suppose that that fluid, a saturated solution, if we want to call it that for the moment, is present in these boundaries in some sort of channels, or maybe even as an adsorbed film or a very thin film, which is difficult to squeeze out. Okay. Then when you have this stress difference, it actually changes the solubility as a function of the normal stress. So the chemical potential, that's the part of the internal energy of the solid which is freely available to drive chemical reactions or diffusive transport. Okay? The chemical potential is part of the internal energy which is capable of driving chemical processes. The chemical potential here is higher than it is here because of the difference in normal stress. So there's a difference in potential, which is that at A minus that at B, and that is equal to the difference in normal stress multiplied by the molar volume of the solid. Okay? So if you like, if you think of it in very simple terms, there's a difference in potential energy of the atoms and ions here compared with there, and that causes them to dissolve, diffuse, and precipitate. That produces creep. If you want to express it in terms of a solubility, you can. This is a rough approximation. The increase in solubility here compared with there is proportional to this difference in potential divided by the gas constant times absolute temperature. So it's proportional. The excess solubility here compared with there is proportional to the excess normal stress. So if you have normal stress gradients, you have the potential for this transfer as long as fluid is present somehow in the boundaries. And there have been many papers using thermodynamics to predict the rate of this type of process, and they all end up with an equation like this, where the strain rate, the creep strain rate, is linearly proportional to the victimic stress, and it's inversely proportional to the grain size cube. So it's very sensitive to grain size. Well, salts have lots of different grain sizes, right? Now, this is the gas constant, this is absolute temperature, this is the molar volume, this is a geometric constant. And this product, D times C times S, this determines the absolute rate of the process. It determines the magnitude of the strain rate. Okay? This is the diffusion coefficient of the dissolved sodium chloride ions in this grain boundary fluid. This is the average concentration of ions in that grain boundary fluid. And this is the average thickness of those grain boundary fluids. Okay? So this is a measure of the mobility of ions in the grain boundary. It has units of meters cubed per second. It's the volume of solid that can be transported per second. That's essentially what this quantity is. Okay? So this determines the absolute rate of the process. Now, tomorrow I'm going to explain how we quantified this in the 80s, 90s, all right? Take it from me now, if you would. This has now a very well-known value. It is also temperature dependent. It has an Arrhenius temperature dependence. It depends an activation energy for this process related to the activation energy for ions to jump through the solution. And what does it predict? Well, if we plot our log stress, log strain rate diagram again with the same old data I showed you before, which is fit nicely by a power law, okay? This model I just showed you, when we actually obtain, from experiments we obtained the value of this DCS, the absolute rate, which I'll all about tomorrow, right? From experiments we obtained that, we could predict what the creep rate would be for this process of pressure solution was in salt with a 3 millimeter grain size or a 5 millimeter grain size. And you see it kind of fills the gap pretty nicely. And if we tip this around now, if we just plot the x-axis as the y-axis and the y-axis as the x-axis, and now we have log strain rate, log stress, I've just flipped it around. You see here it is. This is a prediction, that is the previous typical data for dislocation creep. All right? So, this is predicting that pressure solution will be dominant below, what is it? It's about 5 MPa deviatory stress. Right. Now then came Pierre Berest's wonderful experiments in the Althaus mine. Pierre, I'll say much more about it tomorrow. He really wanted to know what happens in this low stress region. And so with Laura and with Hakim and with Janos and me and many other collaborators, he conceived these experiments in the Althaus mine and also in Geological, and showed indeed that salt creeps with a linear stress exponent and very low stresses. So this is the dislocation creep region, and these data are from, it's a combination of data by Pierre and his team and the Weimos team in Germany and the United States. This is the dislocation creep regime, and here is the transition to a creep with a stress exponent of 1, which you see, right? So, here's the dislocation creep data, here's the prediction for pressure solution, and now when we go to, that was the dislocation creep behavior. Here's the measures, the data points of the measurements that Pierre did, and these are predictions from its pressure solution model for grain sizes that are similar to Poisson. So you see, there is pretty strong evidence that this process really does occur at low stresses. What does that mean? What does it mean if you're an engineer and you're going to have to model the evolution of one of these salt caverns in the far field, in the long term, after shutdown? You're going to need a constitutive law, right? And you need a constitutive law which could be expressed. There are other ways to express it, but one kind of physically realistic way to express it would be to have the strain rate as a sum of a dislocation creep part plus a pressure solution part where you have a linear dependence on stress and an inverse cube dependence on grain size. So if you simply add these two terms together, you can actually describe this data pretty well, provided you know the grain size. And that's the really sad thing, there's masses and masses of data on creep of salt, and lots of it is sort of kind of here somewhere, not very little is down here where Pierre measured these are like 2-year experiments, okay? But there's lots of data in salt, but people just didn't measure the grain size. And you ask them now, where is it? Oh, it's on the way, or we put it in an archive, and now you go into the archive now, and they turn into Christmas trees of salt, sort of growing and effervescing and looking all sort of horrible. All right, that's really a pity. Grain size matters in salt mechanics, and microstructure matters. If you're going to need to do some sort of a numerical model, and you're going to have, you certainly need to consider more than just operational timescales. You're looking at the longer term, far field. Deviatoric stress, low deviatoric stress will be important part of your model. So you need a constitutive law. You can make a nice simple one by adding together this dislocation creep part and the pressure solution creep part, and that will work for a lot of things, and it's been done by several people quite successfully, also matched up pretty well with subsidence data, a few other things. If you want a really sophisticated one, and I'm sure Laura will tell you lots more about this, but one that I like very much is one by Ben Riedlin in the 2022 SaltDeck 10 volume, which includes pressure solution, it includes dislocation creep, it includes transient creep, and all sorts of other stuff. So you have a more complex, more comprehensive model that includes this. You can have a look in there, and I'm absolutely certain that I was going to tell you today or tomorrow something sort of much better still. All right, I'm sort of running out of time quite fast here. I want to come now back to this whole question of these kind of feedback loops and try and give you some idea of the complexity that might be involved here. It might not be. If you have a positive feedback loop here, then there's going to be horrible complexity. The same complexity, on the other hand, might stabilize everything. It might be a negative feedback loop. I don't know, and I don't think any of us do. It's probably going to be up to you, early career scientists, to figure that out. Same goes for the radioactive waste sealing matter. How long does it take disturbed rock salt and backfilled salt? How long does it take to return to the same condition as undisturbed salt, which is what the public would like to have, of course. So I'm going to generalize now and tell you a little bit more about the broader effects of water, and at a pretty basic level. Much of this will probably be new to you, but I hope it will make you aware of the complexity that could be there. Okay? So imagine we have a porous granular rock salt aggregate for a moment. Okay? And we're going to subject that to an applied stress. So this is a representative elementary volume, if you like, or something. Okay? And we're going to subject that to an applied stress at the boundaries. And the pores, they could be filled with brine, or they could be filled with gas that contains some water, okay, some partial pressure of water vapor. Either liquid brine or the presence of water vapor gives you the potential for diffusion. Okay, so if you have liquid brine, you can diffuse ions through the pore network. If you have a partial pressure of water vapor in here, then water molecules will adsorb onto the surface of the grains and create a thin film, which has to be in equilibrium with the partial pressure of water in the vapor phase. Okay? And that thin film will provide a surface diffusion path. Alright? Now then, what we're going to do now is we're going to examine the chemical potential of the solid at the surfaces of these grains. I've chosen a granular aggregate. It could just as well be a dense salt which has got microcracks in it. Okay? It could just as well be not nice pores like this, but cracks. Exactly the same arguments. Okay? Let's examine the chemical potential of the solid at the surfaces of the grains, first of all. So at a location like this, okay, the chemical potential of the solid, which is related to its solubility, is equal to the Helmholtz energy. So that's the part of the internal energy which is capable of doing work, okay, the Helmholtz energy, plus the pressure in the fluid phase multiplied by the molar volume of the solid, plus this term which is related to the surface energy. This is the surface energy, this is the surface curvature, and this is the molar volume. So you can imagine this is a surface tension force, if you like, which exerts a pressure on the surface of the solid and changes its thermodynamic state. You can see it like that if you want to. If you want to think about it in a more sort of statistical mechanics way, you can imagine if you have a flat surface, okay, then the jump frequency of ions and atoms out of that surface is restricted to that half space. You can only jump up like that. Right? If you have a very sharply curved surface, then you have far more degrees of freedom. So the activity of that solid, its potential to react, is a lot higher because the surface is curved. Okay? So surface curvature affects the thermodynamic state of the solid, affects the chemical potential. Right, so we have surfaces all over the place here, these pore surfaces, and of course they're all going to be different, so this is going to vary everywhere around there, just because of the curvature. Not only that, if we've applied a stress on the outside, of course the stress will be transmitted tremendously heterogeneously through this network. So there'll be gradients in elastic stress and plastic deformation and everything else throughout the whole thing. And this, the Helmholtz energy, it is influenced by elastic strength and it's influenced by the presence of dissipations. Okay? So this is influenced by deformation. The curvature is influenced by deformation as well. So you see, there is not, this can vary all over the pore wall surface. More than that, if we now look at a site like this, these grain boundary interfaces, this is similar to what I discussed when I mentioned pressure solution in dense material. If you have solid-solid contacts which contain fluid in a thin channel, microchannel network, or in a thin film, in such a zone, the potential of the solid at these surfaces here is, again, it's equal to the Helmholtz energy, which is influenced by plastic deformation, elastic deformation, and so on, plus this normal stress times the molar volume. So if you have a high normal stress transmitted across here, this term would be quite large. Okay? So you'll have differences between these potential here and the potential out here. So, you'll have differences in solubility, and there's yet another one. Here we go. At the triple junction between two solid grains and a pore, there, the potential right here is again this Helmholtz energy influenced by plastic deformation, elastic deformation. It's influenced by this PF omega term, which is a sort of pressure volume work term, if you like, and it's influenced by the surface curvature here through the combined effects of the solid liquid or solid vapor interfacial energy and the solid-solid grain boundary energy. This term, this measures a contribution to the potential related to the departure from what we call a dihedral angle at equilibrium. If you leave a granular material to reach chemical equilibrium, it will develop a characteristic angle there. And any departure from that is a departure from equilibrium, which contributes to this chemical potential. Okay? So what do we have here? We have an extremely complex microscale system where you have gradients in the chemical potential all over every surface present in there. Okay? Now, for chemical equilibrium, the chemical potential has to be uniform. Alright? So, what can you tell me about this? Can this be at equilibrium? No, of course not. This cannot be at chemical equilibrium in such a situation. There is only one situation in which you can reach chemical equilibrium here. One special case. Can anybody tell me? Come on. When could this be there? When would you have no gradients in deformation, no gradients in normal stress components? When would you have no gradients in curvature? What would be the case? Going. Chemical equilibrium is only possible under fully hydrostatic conditions. That is, when sigma ij, when the stress is basically equal to the fluid pressure. Okay? So this is the Kronecker delta here. Alright? So only when the stress of the solid is isotropic and equal in magnitude to the pore fluid pressure, only then can you have chemical equilibrium. And that means if you apply any stress at all, something will happen. and it will deform, and it will change its microstructure, the pore structure will change, and pretty rapidly in salt. Okay? So all this stuff is going to happen in the wall of a cavity when you're changing pressure and so on. If the fluid penetrates into the wall, these things will happen. Will they have a negative or positive impact? That's another question. It will happen. I'm rapidly running out of time here, so I think I'm just going to jump over a few slides. What I want to emphasize to you is that this equilibrium state, which I just discussed, has been the basis for some very misguided stuff in the literature, which you should be aware of if you were to work on rock salts and look at permeability of rock salt, thinking about transport from rock salt. If you have a truly hydrostatic situation where you reach equilibrium, then you will develop these equilibrium structures. I have to go back. You will develop equilibrium angles at grain contact. And you'll have a uniform curvature. Grain surfaces and pore walls will evolve until you have spherical equipotential surfaces in the classical theory. Okay? So that if this equilibrium angle is, if it's much greater than 60 degrees, it predicts that all these fluid inclusions will be disconnected. If it's less than 60 degrees, they'll be connected. That has been, that classical equilibrium argument has been used to say that rock salt can be permeable if this equilibrium angle is less than 60 degrees. And there have been measurements on that by Lewis and Holness and Gambarzadeh et al. 2013, which caused a lot of reaction in the press because basically they said, well, if you look at temperatures of, something like 100 degrees and pressures somewhere down here, then actually salt starts to get, the pores start to get connected, so salt can be permeable, so it's a terrible place to put radioactive waste. That caused an enormous load of trouble, and it's completely nonsense. So I just want to make you aware of that. It's my personal opinion, but if you read the papers and think, I'm absolutely confident you come to the same conclusion. Right? So this whole argument is totally misguided because, first of all, it assumes that sodium chloride is isotropic. It's not. It's highly anisotropic. The surface energy is anisotropic. So it actually means that this connectivity is far more widespread. Many of these pores are connected anyway. Okay? We also know, as I've just explained to you, if you have a non-hydrostatic stress, you can't have equilibrium. So this whole argument is based on equilibrium. It can't be true. So you would expect these pores are always going to be connected to some extent. Then this is the really important thing here, is that the brine content of natural salt is far too low to have significant permeability. The actual porosity is so low, it's below the threshold needed for geometric connectivity, completely regardless of any thermodynamic considerations. So any stuff that you read in the literature which says that rock salt is permeable because the pores are connected at equilibrium, the pores are connected, yeah, but they're so tiny, okay, that permeability is absolutely negligible. It's only under very special circumstances, for example, if you have dilatancy going on in the salt, you damage the salt, you have microcracks, yeah, sure, it'll become permeable. Then all these processes will start doing their thing if you have water present, and it will evolve. Okay? And then another very important thing which you should be aware of is if the fluid pressure in the cavern rises to a level where it's equal to sigma 3, the least principal stress, then the fluid will start to penetrate the grain boundaries of rock salt in a sort of microscale hydrofracture process. We know that occurs. That's important for permeation of brine. Now, I have way loads and piles more slides to show you, and I'm going to just wind those into 1 minute with other examples. clinician because he's getting restless there, which is quite right. All kinds of things can happen in salt when water is present. This is deformed rock salt with no water, you see dislocations. This is deformed rock salt, which is just 15 ppm water, 50, totally changed microstructure, recrystalline. It affects the mechanical strength. Dry, wet. Okay, and wet means, you know, very small amounts of water. Okay? Just tens of ppm. It's enough to totally change its properties. Pressure solution creep occurring in compaction. You see it, look. Dissolution of grains where they've been in contact, stresses have been high, stressed contacts, precipitation in the pores. Higher stresses, plastic deformation going on here causing enormous pitting and dissolution. Dry salt, strain rate against stress, hardly deforms at all. If you extrapolate these lines down to low stress, right, this is like 100 MPa here, 50, 30 MPa. If you extrapolate this down to low stresses, the creep rate in this particular type of material with these experimental conditions, it's approaching zero. Humidity affects this quantity dCs. We measured it by measuring the electrical conductivity of fluid films adsorbed on the surface of water. So we can quantify the rate of this diffusive transport. And I'm going to skip right up to the end now. All right. What I want to say here is this. Look, if you look at the effect of mean stress or confining pressure, strictly speaking, effective mean stress or effective confining pressure on dilatancy versus the lack of dilatancy in rock salt, you can plot a diagram, differential stress against mean stress, and you have a failure envelope, brittle failure, and you have a region which we call dilatancy boundary. If you go to deviatoric stresses above that, salt starts to dilate. I'm sure Laura will say that. You get microcracks. If you're below that, you get dislocation creep or pressure solution. The key issue that I want you to be aware of from talking about all these effects of water is that once you get into this dilatant field, fluid can get in there, water vapor can get in there, and it will change the properties of the salt. So it will shift this boundary. Very little attention is being given to that. I'm going to go straight to my conclusions. So dislocation creep dominates steady state flow at deviatoric stresses in the range 3 to 15 MPa by time control. It's measurable in the lab. You can make constitutive laws that can be empirical because you can measure it and you don't have to extrapolate it. Linear creep dominates at low stresses by pressure solution. It's grain size sensitive. Constitutive models for the far field and long-term modeling of rock salt, you need to incorporate both mechanisms. You need a two-branch flow law at least. And there are many, many other complex effects going on as soon as you have water present. You can have grain boundary migration. You can have enormously enhanced deformation, multiple mechanisms of healing, competition between damage, healing, and sealing. These effects may occur at cavern walls and during load cycling, especially during hydrogen storage. Water vapor pressure is changing. There's lots and lots of really exciting experimental and couples and THMC modeling projects to do for you, the new generation. Okay, it's up to you to figure all this stuff out. I'll be long gone. And don't forget, a tiny bit of water does a lot. And I want to quote a Dutch idiom. I wasn't born in the Netherlands, I was born in the UK, but I've lived in the Netherlands for years since the Brexit. I'm Dutch. So here's a Dutch idiom. Meten is weten. It means measuring is knowing. Why am I saying that now? I'm saying it now because if you do experiments on rocks, measure the grain size, look at the microstructure, measure the humidity, measure the water content. Otherwise, we'll have another 30 years of ignorance about how this all works. Thank you.
Thank you very much, Chris. Thank you for this wonderful presentation. We exceeded a bit of time, but we started late. Now, of course, I'm sure you have questions. We can Usually there's more for them.
Yes. Thank you, Professor Spear, for this good presentation. I have two short questions. My first question is regarding the pressure solution rate about the TCS parameter. Okay. I know that you promised to come back to it tomorrow, but I understand that this parameter is kind of temperature dependent parameter, and does it mean that we need a TCS parameter for each site we study?
That's a very interesting question. So many people are asking some questions along those lines. Like, we know that dislocation creep behavior varies dramatically from one salt to another. Does this pressure solution parameter, does the rate of pressure solution vary from one salt to another? And my answer to that is probably not very much. Why? Because this diffusion coefficient in fluid, okay, it is a very fundamental parameter. It's not affected much by impurity content. Neither is the solubility of the concentrates, not much affected by impurity content. The key thing which might affect the thickness of the fluid is the absolute amount of water present. Most of our experiments so far, I'll just show you one slide, very fast. Look at this. Okay, so this is a stress strain. These are stress strain curves from constant strain experiments on very dry salt. Okay, 5 ppm water, and this is wet salt, right? 32 ppm, 42, 104. We actually did experiments from 15 ppm up to 300 ppm. It hardly affects the behavior. So I do not think that this will be very sensitive to the salt type, but I can't really underpin that with lots of measurements of different salts. What is absolutely crucial is the grain size of the salt.
My very last question. I saw that you prepared some slide on the self-healing property of the director. I want to know your opinion on this self-healing property of salt.
Sorry, how could I?
I would like to know your opinion about healing self-healing property.
In that case, I'll very, very quickly show that slide. So you're getting me some extra time here, please. Crack growth versus healing. Yeah, so of course you have dilating rock salt, you have growth of cracks, but if water gets in there, these cracks are going to interact. There's going to be healing effects, and here is one such process observed. So this was an experiment conducted by a master's student at Utrecht. This is a cartoon of a crack in a salt crystal. Okay, and what Marcia Huber did was she observed this crack by putting this sample, single crystal, in a microscope and observing Newton's interference fringes through the crack. That's what you see here. So this is looking through the crack. The crack is opening like this, okay? This is the edge of the crack. Here, the crack front. No stress on it. It's in equilibrium with atmospheric humidity at about 75% humidity at room pressure and temperature. And what you see is that over a number of days, the crack heals. Okay, so it shrinks, it contracts. It contracts because mass is transported from here to this side, and crack contracts. And that healing process is pretty rapid. So you see it's sort of the order of 10 microns a day or something. So this self-healing process is quite rapid, and if the crack is very, very thin, it's extremely rapid. Here you see these are really large cracks, monitored in CT imaging over many months, okay, or 3 months in this, or more, in 6 months in this case. You see these cracks healing, becoming disconnected. So this is quite a rapid process.
Maybe a last question.
So feel.
Yeah, I was just wondering, what's your opinion about the fact that when we do tests at the macro scale, we hardly see steady state creep.
Yes.
It's most of the transient actually.
Do you mean at the very low stresses or
All time.
always? Yeah. So of course, to really reach steady state creep, it just depends how long you measure for, really, and then if you measure for so many months and then you double it and you still see that it didn't really reach. So at these temperatures, at the temperatures that are directly relevant to in situ, then you very often will not reach steady state. So actually one has to think of these mechanisms as transient processes which approach a steady state. And if you get nearing, if you get within a range, you have to sort of define what time scale is important for you in order to judge whether or not it would be justified to assume that you've reached steady state. That's the way I look at that. In reality, you're probably, for example, at room temperature, you will never reach steady state. And then it's only a question of, okay, how much stress difference are you talking about on what time scale? So the time scale of the problem becomes important then. Actually, one has to treat such data in a dislocation creep regime as in terms of a transient dislocation dynamics model, which in the limit reaches a steady state. So you can, there are sophisticated models available for doing that, but at the end of the day, it doesn't actually make much difference as long as you define the time scale that you really need to know the strength point. At low stresses, it's a lot more complicated, and the effect of confinement is probably very important. So in the unconfined experiments in the mine, for example, it's quite likely that the structure of the grain boundaries is different from in situ. And how much effect that has is an open question, and something I was hoping to talk to you about here later on, see if we can make a plan to figure it out.
Oh, yeah, I would love to.
So, the break was a little bit short, but well, we are happy to have Philipp with us this afternoon. He will talk about some specific aspects of the geological CO2 storage, sequestration. Indeed, so far, I was mostly speaking about energy storage, but it's already said a few words that, well, we need also think about sequestration of the CO2 that we release industrially. So, well, Philipp, thank you.
Thanks for the introduction and thanks for the invitation to talk to you today here. So during my talk, of course, I will tackle underground CO2 storage. Sometimes people say storage or sequestration. Sequestration it's maybe more appropriate because you want to store the CO2, but you probably won't need to recover it afterwards. So sequestration is where you leave it somewhere in the underground. So in the first part, I want to convince you why we need to capture and remove CO2 from the atmosphere. And then in the second part, we will talk about the technical aspects of CO2 storage in the underground. And then I will show you some of the real-life pilot projects that are currently ongoing in CO2 sequestration. So first, let's talk about CO2 removal in general. So it means generally how to remove CO2 from the atmosphere and how to store it somewhere. Why is this necessary? Of course, you're all up to date with the current climate change issue. So there's a nice website, climateactiontracker.org. They publish regular updates on the current climate change estimations and predictions to recall you every day that how bad our situation is actually right now. So you can see here the most important values from the IPCC agreement to limit the global warming to 1.5 degrees. And you can see that actually right now we are already here. So coming from the pre-industrial average, which is the 0 here, we already have reached about 1.2 degrees of global warming, and this agreement is about 1.5. So I'm not sure if we're going to make this one. And also the predictions different predictions say that with different scenarios that we most likely overshoot this value. You have here different scenarios. The most optimistic one, it predicts about 1.8 of global warming, and the most pessimistic one is the one which includes only the current policies and action that are in place. So with this scenario, we would have very high global warming. And then, of course, in between these scenarios, we have different other scenarios which take into account that only some of the policies are put into action. So if you put this data, if you plot this data with respect to the global greenhouse gas emissions in gigatons of CO2 per year, you can see here this evolution from the 90s, that we increase the CO2 emissions, and right now we are at some kind of plateau. And to be compatible with the 1.5 limit, we would need to reduce drastically our CO2 emissions to a level which is about here, about 28 gigatons per year. And of course, we most likely won't manage this scenario, but currently we are about at some kind of plateau or a slight decrease of our CO2 emissions. So we have a very high target gaps actually here that we have to manage to implement somehow. Also, what I find nice here in this graph is that we see here this little kink which is going down, and this is due to the COVID in 2019. And what is nice to see that is that this kink actually takes the right direction downwards. So to manage this gap, we should modify our daily living to reduce our mobility and our consumption, similar to what happened during the COVID-19. Well, so now we have different scenarios that need us to reduce our CO2 emissions, and all these different scenarios are plotted here. So here to manage the global warming to 1.5 degrees, we need until 2050 have reduced all our CO2 emissions to 0. So of course we have some variabilities because all these different curves are different prediction scenarios which are difficult to realize because we have so many factors that are involved in these estimations. But all of them go more or less through a 0 at 2050. So this says that we have to reduce our net emissions, which includes which is the sum of our anthropogenic emissions and together with the amount of CO2 that we can remove also from the atmosphere. So why do we need both of them? Why we can just reduce our CO2 emissions? You can see here that there are two of these different scenarios. So from this curve now, they have plotted two specific scenarios, the P1 and the P4. And you can see that in the P1 scenario, we reduce our emissions, which is the gray part, but it doesn't get really to 0. There are still always some positive CO2 emissions in this scenario. So to be at a net 0, we need also the brown part, which is CO2 removal. And the same thing happens in the P4 scenario. So in this scenario, we are able to reduce our CO2 emissions almost to 0, but to arrive at the 0, we also need some CO2 removal. So our biggest job is actually the gray part, to reduce our energy consumption. We have to decarbonize electricity and other fuels, and we have to reduce agricultural emissions. But in addition to that, we also need to remove CO2 that is already in the global cycle. And here you have some numbers from the IPCC report, which say that we have to remove around 100 to 1,000 gigatons of CO2 within our century. So why we have to remove it? Why we can't just reduce our CO2 emissions? Because if you look at the life cycle of any energy that we have. So here you have printed different energy sources, so renewable energies like geothermal energy, photovoltaic, and biopower. Also you have nuclear energy here, and here are fossil fuels. So if you look at the life cycle of all of these energies, you will see that even the renewable energies, they include some of CO2 emissions due to the production of solar panels, for example, due to the transport, the installation, the infrastructure. So even all of these energies, they have a positive CO2 footprint. So even if we can switch completely to these renewable energies, we have to remove the CO2 that they still emit, right? So the optimal scenario would be to eliminate completely this part here, which emits a lot of CO2, then switch to the renewable energies, and all of the positive CO2 that is still present here, we have to remove with CCS, that means carbon capture and storage. I put here a small question mark here because the nuclear energy is somehow in between the both of them. In terms of carbon emissions, it's quite a positive form of energy, but then you have other natural issues with the nuclear energy because of the waste that it generates. So now, with these IPCC emissions, there are some predictions that if we want to achieve the net zero emissions until 2050, we have to store a lot. We have to first capture all the CO2, and then we have to store it somewhere. And these estimations, they tell us that we have to store, by 2050, 7.6 gigaton of CO2 per year. So it's a huge amount. So now we have to think about different methods where to store all of this CO2, right? First of all, we can look at the carbon cycle at our planet, because you have to keep in mind that CO2 is not something that's only human produced, but the CO2 is already in the atmosphere naturally. It's produced by different sources and is also captured by different mechanisms. So for instance, you have so mostly the CO2 is emitted from the vegetation and from rocks, for instance, from weathering, from volcanism, and from freshwater outgassing. So you have some CO2 emissions. All the black parts, they are natural CO2 emissions. So this emits CO2 to the atmosphere, which contains a certain amount of gigaton of CO2 already. And then you have also some uptake of this CO2 due to the plants and mostly biological uptake. But then there are our human intervention, which are the red parts, which add more CO2 to the atmosphere that we want. So we have to eliminate these sources and capture also the CO2 somewhere. So the literature and previous research has identified many different mechanisms or different techniques how to remove CO2 and how to store it also, because there's always the two aspects. And you can see these different technologies here plotted in the right graph, and which indicates the cost and also the potential in terms of CO2 masses. And you can see that the most important one, the biggest one here, is the DACCS, that means direct air carbon dioxide capture and storage. It means we have to take out the CO2 from the air somehow and then store it in the underground, because there's the amount of CO2 that this technology covers is so huge. The only reservoirs where we can put it safely is in the underground. We'll come to that later. Then we have another technology that is a little bit cheaper but also covers large volumes. It's bioenergy with carbon capture and storage. So here, in contrast to the DACCS, you capture the CO2 not by filters or artificial methods, but by plants. So you plant something, the plants, they recover the CO2, and then you burn the plant and directly store the CO2 somewhere. So it's something like the plant will be your CO2 filter, which absorbs the CO2. So this is a little bit cheaper because you eliminate the artificial filters and covers the same amount of CO2, because finally you will store this part of CO2 also in underground formations. Then you have the classical method, which is afforestation, reforestation. So also the plants or woods will capture CO2 naturally. You have soil carbon sequestration. That means through agriculture. And also biochar, which is some kind of organic soil fertilizer, which is also capable of absorbing CO2 and adding it to your agricultural activity. There's another technique that is called enhanced weathering and ocean alkalinization. So here you have some chemical decomposition of rock which absorbs CO2. But here also the disadvantage of this technique is that you would need large surface in order to have an efficient chemical reaction of the atmosphere with the rock that you disperse somewhere. And the last thing that I added here, but it's not in the graph, is the ocean fertilization. This was a technology that was proposed recently, but I think they dropped it because this involves that you add like biological, like plants or plankton to the ocean, which can also absorb the CO2. But I've read that the recent studies show that this perturbates a lot your natural cycle, so I think they dropped this technology recently. So as I said, the biggest part here, so the two technologies, DSCCS and BSCCS, both of them involve geological storage. So this is a very important factor. Geological storage is the most important factor in our carbon removal systems. So that's why we talk about this today. And the first thing that we want to look at, if we handle CO2, is of course the physical properties of CO2. Right? So I will start with some dry properties of CO2, but we have to take them into account if we want to manage this kind of fluid. And here we have some different aspects that are mostly positive, because CO2 is not explosive, non-combustible, and odorless, so it's quite moderate to use it. It's heavier than air, so it can put the danger of asphyxiation, and it's non-toxic. Only if you have too large amounts of CO2 in the atmosphere, of course it can asphyxiate because of this. And you have to take into account that CO2 is already, as I said, part of the global carbon cycle. So it's already present in the atmosphere. And if we handle it, and if there are any risk of leakage, it's not a huge issue because there's already CO2 in the atmosphere, right? So now I come to the physical properties and the different states of CO2, which are very important if you want to store it in the underground. So this is in this diagram here you will see the pressure and temperature and the different states of CO2. So you have, as for any type of fluid or matter, you have solid, liquid, and gas state. And you have here these delimitations between these different states. And you can see here that you have a solid CO2 at very low temperatures for any kind of pressure almost. And then once you have like ambient temperatures, the CO2 will become liquid or gas depending on the pressure that you apply, right? So this is not something quite special. You have this kind of behavior for many kind of fluids, for water, or for natural gas, for instance. But then there's another phase, another kind of state, which is above here. I'm not sure if you have heard about this, but this is called the supercritical region. And the supercritical region you reach when you go above a certain critical point. So critical point means a certain pressure and a certain temperature. And for CO2, this is why the supercritical region is very known for CO2, because for CO2, this critical point is very low. The supercritical point exists also for other kinds of matters, like for water, but for water it's very high, so you never hear somebody talking about this. So that means once you go above about 31 degrees and about 7 megapascal of pressure, your CO2 will go into a supercritical state. Okay, now this is a very abstract word. I'm not sure if you can imagine something about supercritical. The most important thing is that it becomes very dense and very soluble in water. But of course, if you hear supercritical, you might want to imagine something to understand what's happening. For this, I have some kind of, I put here a video from the colleagues from Dresden. And what they did, they have constructed some kind of pressure vessel that you can see here with a transparent glass. And inside there's CO2, which is first, I think it's in gas form. And now they will go to, it's in two phases. So first they have it in liquid and gas form. And this vessel they will heat up and also apply pressure to it to go into the supercritical region. Let's see. Okay, so they are already in the right pressure region, and now they will only need to heat it up. So the pressure is already above the necessary one, but they need to heat it up with this heater here. And you can see that it's starting to boil. So it's going from liquid to supercritical already. And the more they boil, I think behind here you can see the temperature, but it's not, theoretically you can see it. And what's happening is that the liquid CO2 will go to the supercritical state, which is some kind of state in between liquid and gas. So it means the fluid has a similar density than to a liquid, but it has properties of gas. That means it expands and takes up all the space possible. And you can see it here. Now it fills everything up. And you see it become kind of cloudy also. And then I can speed up a little bit. And now what they do is they cool it down again, so you can see recondensation, and it will separate again into two phases. Okay. So now you wonder why I'm talking about this. It's quite interesting to look at, but why do we care about this for CO2 storage? So I talked about density, and density is very important for storage efficiency, because the denser you can get your fluid into, the more of the mass you can store in a given volume. So this is nicely illustrated here in this figure. Like, imagine that you have a balloon of a given volume of CO2, and now you compress it because you inject it underground, because you have the natural pressure gradient. And now you compress it, and because you also have the temperature gradient, which increases the temperature naturally the deeper you go, you increase both of pressure and temperature. And at some point, your CO2 will reach critical state naturally, which is nice because now the density increases a lot more, so non-linearly, that you can see here. So we are able to store huge volumes of CO2 in a given volume, and huge masses of CO2 in a given volume. And this depth here is that you can estimate it roughly, because you know roughly your pressure gradient and you know roughly your geothermal gradient. So the conditions for the supercritical state of CO2, which occurs here, is approximately met at around 800 meters of depth, which is nice because this below 800 meters, you often find natural reservoirs that exist, that are accessible by our technologies. I showed this more in detail here, so you can see here different range of geothermal gradients that we expect in nature, depending on the location and different rocks that we have in the underground. And you can also see the increase of density of the CO2 now, and the change from vapor to liquid, depending on the different temperature gradients. But most of them have the change of phase at around 800 meters of depth. Okay, now we know that we want to get our CO2 in the underground. Now, of course, we need to consider many different technical aspects in reservoir engineering to assure a safe reservoir and an efficient operation. Of course, now let's see what are the main ingredients of our underground reservoir. So what are the elements that we need to consider, that we need to look at for safety and efficiency? So in most reservoirs, of course, we have our injection well that we have to drill to get our fluid in the underground. We have some kind of reservoir rock. We have heard this in the first session yesterday, so we need a large enough pore space where we put our gas into. And of course, because our gas is lighter than the fluid that is present naturally in the underground, most often it's brine, the gas wants to migrate by itself up again. So this needs to be prevented by some natural structure. Often, so we need some low permeable rock that is already present there with a kind of anticlinal structure to block this kind of gas bubble in the underground. Okay, and most often these low permeable rocks are either clay rocks or sometimes also salt, because we have heard about today that it has a low permeability, so it avoids the migration of the gas in the vertical direction. So this cap rock provides the isolation. It's important, of course, for the safety and also for the efficiency, because if we inject the gas in the underground and it comes back up again, we have invested the money for nothing, right? And also the rock, the storage rock itself needs to be considered, because this governs the efficiency of our reservoirs. We need a high porosity, because the porosity will define the amount of pore volume, the amount of gas that we can inject into it. It needs a high permeability. We need to be able to inject it easily in the underground. And we also need to be able to displace the fluid that is here naturally, because once we inject the gas, we need to be able to push away the brine that's located there. And other safety aspects that we have to consider, as I said, we have to check if the CO2 that we inject in the underground is not leaking somewhere and coming up to the surface again. More for efficiency reasons, as I said, but for safety, because even if it would have some leaks here, the CO2 in the atmosphere is already there. So even if it leaks, it doesn't. It's not very dangerous for humans. We need to estimate how much CO2 can be injected in a certain site to estimate its efficiency, and we need to assure also that the CO2 stays there for long time scales. Because, of course, during several years we will have the operation where we inject our CO2, but at one point we want to close the well and abandon our site, and we would like that our CO2 stays there in the underground also after several tens, hundreds of years. Okay, we come back now to different aspects, more or less in detail. First, all the safety aspects I won't tackle in details, because we have heard about this a lot in the previous session. So these are all different geomechanical aspects that you need to consider for any kind of underground operation, for underground hydrogen storage, for underground storage of nuclear waste, also even for geothermics. We have heard about different aspects in the previous session already. For instance, if you inject your fluid somewhere, you need to consider the subsidence or heaving due to the stress changes that you induce. You need to assure that there's no fault reactivation, as this explained to you. And we need to take into account also thermo-hydro-mechanical couplings, because the CO2 that you will inject somewhere, it has a ambient temperature mostly, while the temperature in the underground is due to geothermal gradient, like 30, 40, 50 degrees hot. And you also have chemical aspects to consider, because when you inject the CO2, it can react with the rock or also with the wet cement that you have installed. So you have to take into account all these thermo-hydrochemical reactions that can occur when you put your CO2 in the underground. When you have assured all of these safety aspects, you know there's no danger for the human life on top. You also want to consider economical aspects. So how much CO2 can I store in my site? All right. So let's say we have now estimated with some geophysical measurements the approximate geometry of our reservoir. That means here I just put an axis symmetry. So let's say we have here a well and we have a reservoir. Due to the cap rock, we have some anticlinal structure, and that means if we inject here the CO2 in the underground, we can fill up here this reservoir rock, which is illustrated here in blue, which is filled initially with brine. So now think about how can we know this volume, but what is the volume of CO2 or the mass of CO2 that we can inject? What are the important factors? Are we able to fill all of this volume with CO2? Actually, we have to consider that we have now a porous medium with two different fluids inside. So we have the brine, which is there naturally, and we are coming with our CO2, and we want to push the brine out of the rock. But it's often not that easy. You might remember from soil mechanics, unsaturated soil mechanics, that you have this capillary pressure curve, or also the suction that you have in soils, which is dependent on the water saturation. Okay. Let's now take our rock in the natural state, which is fully saturated with water, right? So we are here, and there's no pressure, nothing. Now we want to inject the gas with a certain kind of pressure, so we need to increase the pressure of the gas to make it enter the sample. That means first we have to increase the pressure, and at some pressure we see that a small amount of gas will enter the rock, and the more we increase, at some point, which is called in reservoir engineering breakthrough pressure, we'll see that we have a continuity of the gas through the sample. So at a certain pressure, you will see this non-linearity here in the capillary pressure curve. You will see a lot of volume of gas will enter the sample and will traverse the sample to the other side. And the more, of course, the more you increase the pressure, now the more you will be able to saturate your sample with the CO2. But as you can imagine, you have in natural materials often very small pores. So depending on this pore structure, in most cases you won't be able to fill all of the pore volume with CO2. That means that the more you increase the pressure, you will reach a certain threshold, which is called here the irreducible water saturation. And this threshold means that there are some small, very small pores, which will be always saturated with water, right? And of course, this curve can look differently for different kind of materials, which depend mostly on the pore structure, but also on the type of minerals constitute our porous structure. So we have to take this into account because, of course, it means that we won't be able to fill all of our rock with CO2. And what is also important for our application is something that you can measure in parallel to this curve, is the relative permeability. Relative permeability will be important when you want to know how much pressure we have to apply to fill our reservoir with the CO2. Because you can imagine that in the beginning, when we are completely water saturated, the relative permeability of the gas is 0, CO2 is 0. And the more we fill it with CO2, the permeability of CO2 will go up, but the permeability of brine will decrease, right? So these two ingredients are very important to be able to simulate our reservoir rock with respect to the migration of two different fluids that fill the pores. Now we can do this quite easily with, for instance, poro-mechanics, where we just use two fluid phases, and we have this interaction between two fluid phases. So the capillary pressure, the difference of pressure between the two fluid phases, and also the relative permeability that we can inject, for instance, in our Darcy's law, to modify the permeabilities of each of the fluid phases. But now we need also to evaluate this. We need to think about how we can evaluate these properties in the lab, right? I just give you a small outlook here, because we can do this with the devices that we have seen before in the previous sessions. You can imagine a triaxial cell where we can inject now from the top and the bottom. You have a cylindrical sample and you can inject different fluids from the top and the bottom. This is normally used to evaluate your permeability using Darcy's law, right? And now you just take two different fluids, for instance CO2 and water, and you can inject them at the same time in different quantities. So this will allow you to saturate the rock sample with different degrees of water saturation. And when you measure the difference of pressure between the inlet and the outlet, so the difference of pressure between the gas phase and the water phase, you're able to measure your capillary pressure. And at the same time, you do this by measuring the inflow and the outflow and the difference of pressures. You can establish your relative permeabilities, right? Because you know what inflow, what amount of gas, what rate of gas flow you have and what rate of water flow you have with respect to different gradients of pressure. Yes?
You mentioned that below the depth of the 800 meters, the CO2 will be supercritical state.
Yeah.
So I would wonder whether the Darcy law is still suitable for the supercritical CO2.
Yes, yeah, it can be applied. But Darcy's law is it's an empirical law, but it applies also for supercritical CO2. But it behaves in this case like a gas. So it's considered similar to gas because it takes up more space and has similar viscosities also to gas. And so you can measure these macro properties in experiments as we have seen before. You have your centimetrical sample, but you can also try to understand the physics behind these properties by microscopic tests. So what we often use in the lab is mercury intrusion porosimetry. This allows you to characterize the pore structure and then through some kind of advanced models to recalculate this capillary pressure curve and the relative permeabilities based on the microstructure of the material. And you can do the same thing also with 3D imaging, for example, with X-ray microtomography or NMR scanning methods. You can reconstruct your pore structure and then try to back calculate these properties. I'll show you an example how to do this here. Because the capillary pressure curve, this one, it's emerging because you can imagine that your rock samples have different kind of pores. which can be explained as different kind of capillary tubes next to each other. You can see this here. That means when you apply different pressures here, you will feel depending on the pressure and the diameter of the different capillary tubes, you will fill more or less different kind of tubes of your material. So globally, you will have a capillary pressure curve where in the beginning you don't fill any of the tubes. At some point, you start to fill the larger ones, and the more you increase your pressure, will always also fill your small tubes, right? So what people did then is to use this theory to reconstruct real pore structures that are obtained, for example, from X-ray tomography with what they call pore network models. So that means they replace this real geometry with a network of balls and interconnecting tubes based on the real geometry. So there's some kind of abstraction needed between the two. But once you have your 3D pore network model, you can do a simulation where you inject fluid from the one side, and you can obtain the same kind of capillary pressure curve that is obtained from macro experiments. So this interconnection allows you also to validate your macroscopic observations and also explain what you see at the macro scale, to explain the macro behavior through microscopic observations. Now, we have partly answered the questions: how much of our reservoir can we fill with the gas, with the CO2? Because, as you remember, even when we apply very high pressure here, we will not be able to fill some of the pores. That means, in a given volume of porous rock, we will have already a great part which is filled by the solid matrix. And then we have the pore volume, which is only partly filled with the CO2. So you can imagine here that if you have a given volume of reservoir, you can only fill this part with CO2. So in the calculation, the easy calculations, I want to spare you today with complicated equations, so I put a quite easy one here. So to estimate the storage capacity of CO2 mass, of course, the important factor is the density. We can get to supercritical density. Then we need to know the reservoir volume, of course, which is important. Then the porosity is an important factor, but then also the maximum saturation degree is important, because the total porosity, you will only be able to fill partly this CO2. Okay, now we know that we can roughly estimate our storage capacity, but how does the CO2 migrate in reality? Let's go like this. Now, if you look at real reservoirs, you also have to consider other factors which make it even more complicated. Because, of course, you have gravitational forces. That means if you inject the CO2 here, due to the gravitation, to the buoyancy of the supercritical CO2, it will move upwards. So you have, first of all, a distribution which looks more like this, all right? And then, if you look in reality, you have different other forces that are in place, which makes everything much more complex. So you have, first of all, capillary forces, as I said. You have viscous forces, and you have also heterogeneities, most important in permeability. So you can imagine easily, if you have some zones here which are less permeable, of course, the CO2 will first migrate into the zones which are more permeable, and which gives you some heterogeneous pattern. The capillary force and the viscous forces are more difficult to imagine right now, so I will explain this to you in the next slide. So some researchers, they identified the different kind of forces, hydrodynamic forces, that exist if you have two-phase flow in porous media in general. And they identified this quite particular hydrodynamic behavior with different regions of fluid migration behavior. So the most common one is the stable displacement. That means if you inject into your porous media from one side, so you have one fluid which saturates the medium initially, and you inject the other fluid from the one side, you will have a quite homogeneous front, injection front, that is propagating through the medium. So this is a stable behavior. This is what we want to achieve in our reservoir, because the stable behavior will allow us to control and to predict where our fluid is going. But then they have identified other regimes, which are called here viscous fingering and capillary fingering. And these two different regimes, they depend on the viscosities of our fluids and also the capillary structure of our pore network. And I will explain this to you separately. First, the viscous instability is something that occurs when you have two kinds of fluid, even without a pore network. So even if you have just two types of fluids which you want to mix with each other, you can have some viscous instabilities that are occurring. This is quite nicely illustrated here in an experiment they did. They put together two transparent glass plates, and they have filled the space between the plates initially with one kind of fluid, and from the center they inject another fluid with a different viscosity. And what they see is that if the viscosity ratio, so the difference between the ratio between the two viscosities, is high enough, you create flow instabilities. So instead of creating a front between the two fluids which is readily homogeneous, you have this kind of instabilities that occur. And of course you want to avoid this behavior in your underground reservoir, because any kind of fingering, it will make your fluid go in directions where you can control, where you can predict it. It is even more important for CO2 storage. This is less important than for hydrogen storage, for instance, or natural gas storage. Because for CO2, you just want to get rid of the gas, get rid of the CO2 in the underground. But for gases that you want to recover, again, it's even more important, because if they migrate in regions where you can't access them later on, they are lost. So you want to avoid this kind of fingering instability. So the viscous fingering, you have to keep in mind, it depends only on the difference of fluid viscosities. So there's no influence of the pore structure itself. But there's another kind of instability. The pattern is the same, it's similar, but this instability is due to the capillary pressure of your pore structure. And this is illustrated here with the capillary number. So here in the capillary number, in this equation, you have again the viscosity of the invading fluid that you inject. So in our case, it will be CO2. And here also the flow rate, so the injection rate plays a role. And other parameters that are the interfacial tension and the contact angle. So these are properties that are related to the capillary forces. So depending on the type of rock that you have and the kind of diameter your pores have also. So if your capillary number is very low, that means you can create capillary fingering. You can see this here. It's illustrated with a calculation with a method that's called Lattice-Boltzmann method. It's a kind of simulation method that allows you to calculate hydrodynamics. So with Lattice-Boltzmann method, you can reproduce this kind of hydraulic instabilities. So if you inject here and you have a low capillary number, you also create this instability pattern. If your capillary number will be high, that means you will have a stable displacement in the front that is really homogeneous. This is something that we want. That is something that we want to avoid, or we want to predict this. And we can control this one by adjusting the injection rate that we impose in our reservoir. There's another hydrodynamic instability that's quite interesting, also to illustrate here. And it is something that you can even observe at home when you mix two different fluids which have different viscosities. And because of their different densities and the buoyancy, they will create some hydraulic instability. So here you can see that there's one fluid that's already present, and they fill the recipient with another fluid that is heavier and it wants to sink down. But instead of having a homogeneous fluid migration, you have instability that is recorded. And what's interesting, keep in mind, if you talk about salt, you often see natural occurrence of salt in dome form. And the domes form exactly because of this kind of instability. Because the salt has a lower density than the overlying rock, so it creates this kind of unstable structures. And this can also occur in your reservoir if you have two different fluid densities, CO2 and the brine that is there naturally. And of course, you can have other phenomena that can influence the migration of your CO2 in the underground. Something that we have seen also in the first session. If you have some mechanical or chemical interaction of your injected fluid with the rock structure. So, for instance, here, if you have in soils, it can happen that if you increase your injection pressure, that your grains are moving, so you increase your permeability, and this in occurrence increases your flow, so you can have some kind of feedback cycle, some kind of coupled behavior between the hydraulics and the structure of the pore structure of the material, where it can again increase the permeability. And you can even accentuate this behavior if you have a chemical interaction between your fluid and the rock, as we have seen in the first session. So if your injected fluid chemically also degrades your material, you can form even wormholes or preferential pathways of your fluid migrating through the material. So all of these aspects you have to consider when you design your reservoir. So when you know your site, you identify your site, you need to take into account these different aspects when you want to predict how your CO2 will fill the reservoir and where it will go. But a particular thing about, so this is the same theory that is often applied to any kind of underground injection problems for oil and gas and also for natural gas storage. But now what is particular about the CO2 sequestration is that we want the CO2 that we inject to remain in the underground, right? So I put there a nice illustration of SodaStream. I do some advertising for them, but this is one kind of mechanism of trapping of CO2 actually. So when you make your soda at home, you're actually contributing to CO2 storage. Because what you do is to take gas, CO2 in gas form, you inject it into water, and then if you put it in the fridge, it's there and sequestrated. So actually,
we drink it.
You shouldn't drink it actually. Just keep it there. But what we are doing is actually you dissolve CO2 in the water, and this way it can be stored. So this is also one of the trapping mechanisms that is essential for CO2 underground sequestration, the dissolution. And actually they have identified 4 main mechanisms of trapping. So the trapping is an essential part for the long-term sequestration of CO2. We need to assure that the CO2 stays there through different kind of mechanisms. So the first one is the structural trapping, which is important. The first right after the injection. And the more the CO2 stays in the underground, you will also have residual CO2 trapping, which will become important. And in the long term, we have other mechanisms, the solubility trapping and the mineral trapping. Solubility trapping is the soda stream, and I will explain all the other ones in the next slide, okay? So, structural and stratigraphic trapping is the trapping mechanisms that is important right at the beginning. It's the one that I showed you also in the previous slides, where you need some kind of lithographic structure that keeps the CO2 in the underground. So this is the most important trapping mechanism. That means you can have some anticlinal structure, so the CO2 bubble stays at a certain place, and you just need to pay attention to this location. It's called spilling point. It's where the CO2, if you put too much into the reservoir, could escape and could move somewhere else. You can have these impermeable structures through low permeability rocks, but also through faults. Faults in the direction perpendicular to faults have a very low permeability, so they are also able to block the migration of CO2. But also there's another case where you can have some long stratigraphic structure which have no anticlinal, but even then they can allow you to store CO2. But there the main trapping mechanism won't be the structural trapping anymore, but the other trapping mechanisms that I will explain further on. So in this kind of structures, you want to inject your CO2 and your bubble will be able to move. But you will rely on other trapping mechanisms that the CO2 stays there. Okay? So the second most important trapping mechanisms in terms of time evolution will be the residual trapping. What is residual trapping? If you come back to the capillary pressure curve that I've shown you before, actually I've shown you only the first part of the capillary pressure curve. It was the part where you inject CO2 into your rock. But there's also a second part of this curve. The behavior, once you have injected your maximum of CO2, if you reduce the pressure again, what will happen is that the CO2 gas will flow back, but in many cases, you won't increase the water saturation again to 100%. Why is that? Because if you look to this illustration here, often you have some bubbles that will remain inside, even if you increase the pressure, and even if you suck on your sample, these bubbles will be trapped inside there because of capillary forces. It's even occurring in your water bottle. If you have CO2 in there, you open the bottle and the bubbles will flow up, but you often have bubbles that are blocked on the side, right? They will be stuck there. And also this is due to capillary forces because of the small friction, the interface tension between the glass bottle wall and your bubbles will keep the bubbles there. And this is something that is very positive for our CO2 storage, because the higher the volume here, the more CO2 will be trapped in the rock, even after we abandon the well and even after we remove all of our pressures. And this can be illustrated also here in this image. So imagine that you inject your CO2 here in the reservoir. So you will increase the pressure, you will saturate your rock with CO2, but at one point you will stop the injection and you will abandon your well. And the CO2 will, due to the buoyancy, it will move, so the bubble will go up. So it will move through with its pathway, it will traverse a large volume of rock. And this is quite advantageous because throughout all its pathway, it will leave some of the bubbles trapped in the rock. So even at some point the bubble will the most part of the bubble will stay up there, but you will also have some of the smaller bubbles that are trapped in the pores that will remain here. This is kind of an efficient procedure because imagine that you have a very long stratigraphic structure. You inject at some point and you let your bubble traverse over, that it migrates through a very long pathway, and throughout all its pathway it will leave some bubbles trapped. So we have talked about stratigraphic and residual trapping, and the third one is solubility trapping. We have seen this. Because we can chemically dissolve CO2 into water, we can store even more amounts of CO2, even above the amount of supercritical CO2 that we inject. Because the CO2 can dissolve into the brine that is present there naturally, which the dissolvability depends on the salinity, on the temperature, and the pressure. So what happens is that, you have seen this before, we inject here through the well, you will have this kind of migration of the supercritical CO2 that moves a little bit upwards due to the buoyancy forces, and also the lateral direction. And we have the main bubble of the CO2 that is here. And with time, what will happen is that at the contact between CO2 and brine, you will have the dissolution. And what happens is that water or brine that contains dissolved CO2 will be heavier than the water that contains no CO2. And this is nice because the CO2 saturated brine will sink downwards. So this will create some kind of convective movement. So the saturated water will move downwards, and the unsaturated water will be in contact again with the CO2 here. So you will automatically create some movement where you will always dissolve more and more water, and the water that's already saturated will go downwards. And this, by the way, creates also this nice instability structures that I have shown before. So theoretically, over a long time period, in this scenario, you will be able to dissolve, so to saturate all the water with CO2 due to this density difference. And what they scientifically the dissolved CO2 is considered to be permanently trapped. So this is nice, because even due to pressure changes, it won't go to the surface again. It will stay in the water, and it allows us the storage of very long time scales. So the solvability trapping, if you look at the first graph, it's the one that becomes important at very long time scales and even increases the longer you go. And there's a fourth mechanism. This is called the mineral trapping, and this is just basically the precipitation of CO2. So what happens, first of all, if you dissolve the CO2 in water, you create carbonic acid. And this acid will react with some of the minerals, calcium, magnesium, and iron, that are present often in many of the reservoir rocks. And this will precipitate different kind of minerals. So you will transform the CO2 that is first in supercritical state into solid CO2 that is trapped there for eternity. Right? To be able to simulate this is a little bit more complicated, so you need some geomechanical models that take into account chemical interactions, and you can take into account this reactive transport through models that exist already. But some of them need to take into account also microstructural changes. This is the thing that we have seen in the first session, that due to precipitation and dissolution, you can change also your rock structure, which can lead again to deformation of your rock matrix, or also changes in the permeability of your rock. So now we have talked about the different trapping mechanisms. So these are the most important things that you have to keep in mind when you want to assure the long-term trapping of CO2 in a certain site. So you need to first evaluate, of course, the structure of your underground stratigraphic layout. Then you need to investigate the composition, the microstructure of your rock, to know how the CO2 migrates through the reservoir rock and how much you will store there through the residual trapping. Then you might want to do some reservoir simulations where you take into account the dissolution of CO2 into water over long time scales to see how much of CO2 will be there through dissolution. And then if you also want to take into account the mineral trapping at very long time scales, which is even more advantageous than only the other three, you need to model also the geochemical interactions of CO2 with the rock minerals. So these are the most important parts that I mentioned here. We need to take into account the CO2 properties at depth that I explained in the first part. Then we need to know the rock properties and also the architecture of our layout. We need to take into account fluid dynamics. This is what I said, permeability, capillary forces, also the capillary instabilities that govern the migration of the CO2 bubble. And for the long-term behavior, geochemical reactions, which can also influence the mechanical stability of your reservoir. How am I with the timing?
20 minutes about.
Okay. So I might finish a bit earlier. I give you just the outlook of different real projects that are currently ongoing. So keep in mind that, I said in the beginning, we have a quite high goal, target storage of CO2, which is plotted here. So in 2030, to have net zero emissions, we need this amount of stored megatons of CO2 per year. Okay? And compared to this, we have the currently operating CO2 storage sites, which is in light blue. I will show you this project right afterwards. And we have some other sites that are in development. Okay? So, call to you all. You have some tasks to do here in the coming years. Because to fill this gap between here, there is much more research and also politics to be done. I will show you why it's a proven concept, because we understand most of the physics behind, but of course we need pilot projects also to prove the feasibility on site. So there's one of the operating sites in the light blue that is currently ongoing and is actually storing CO2 continuously. And there are other projects that are currently in development that are planned. So to summarize this, our current challenges is we have the knowledge to store CO2 in the underground. We know that it can remain there trapped through the current sites that are ongoing. But what we need to improve the efficiency. So we need to store larger quantities. We need to improve the trapping, and we need to optimize the operation monitoring technologies to make it cheaper to store CO2 somewhere and to make it more attractive also for the industry to take the CO2 there and to invest money for that to be stored somewhere. And there are some current pilot projects that are going on in basalt rocks. So in basalt rock, there's one particularity that basalt rock is really reactive with CO2. So compared to the graph that I showed you before, which is the classical graph for like sandstones and carbonate rocks, if you inject in basalt, due to the high reactivity of the basalt with the CO2, the mineral trapping will become really important. And this is really advantageous because it will allow you to to care less about all of these mechanisms and to rely really about on the reaction of the CO2 with the rock that is there. So this is part of a current project, CarbFix, that I will show you in the following slides also. I will finish my talk with these actually 2 project sites that are currently running. This one is the CarbFix site in Iceland, which is quite beautiful because you have the green landscape behind. There's some geothermal power plant right behind it. So to fill all to have only the renewable energies here inside, they also store the CO2 here in a project site. And what is nice to see is that your storage site has a very small footprint. So you only need your well here and you inject your CO2. So it's quite nice, even if you design your wellhead with some industrial designed head here, it's even more beautiful. So actually the blue one that I showed you before here, that's currently ongoing, this is the Sleipner project. This one is located in the North Sea, so here between the UK and Norway, and it's the world's largest and also first storage site of CO2. It was established in 1960, and it's located right in a zone where you have already several petroleum fields in the North Sea. So actually they didn't even need to, they have already a petroleum platform there, and it's here where they installed a CO2 storage site. So you can see this here in a cross section. On the top you see the North Sea, you have the offshore platform here, and so historically they have constructed this platform to exploit the Heimdall formation, which is here at 2,500 meters depth, with several wells where they extract, I don't remember if it was natural gas or petroleum. And then they decided to construct this pilot project right next to it from the same platform. And they actually, it was advantageous because they had some knowledge of this sandstone formation that was between the Heimdall formation and the surface. So in this sandstone formation, which was porous enough, as you remember, you need a porous rock because we need to inject large amounts of CO2. So they selected this sandstone formation and they constructed this horizontal well inside it. And from one point here, they started to inject the CO2 inside this formation and see if they managed to store it there. Right? It was the first pilot project. So what they have done is, of course, with some preliminary, prior to the injection site, they have studied extensively the rock that they found here, the sandstone, and they have also carried out parallel geophysical measurements of this injection site to see how the bubble will behave. And this is what you can see here. So these are some measurements that they took from the boat on the North Sea. They did some geophysical measurements to scan all the formation over a large depth. You can see here it's kind of abstract, so if you're not used to see the bubbles, even me, it's not very easy to identify, but you can see here this was before the injection. So you see here the different layers through the layered rocks. And once that they started the injection, you can see here that some changes occurred. So this is due to the presence of CO2. They measured here a difference of their ultrasonic waves that are going through. And of course, because they are injecting continuously in this site, so the bubble of CO2 there, it will continuously grow. So they monitored this, and you can see that over the years ongoing, this strange zone here is getting larger and larger. So they are able to quite precisely measure the location and the extension of the CO2 bubble. And also, if you take a cross section here, So this is the vertical cross-section. If you take a section here in the yellow line, you see this extension of the CO2 bubble in the horizontal plane. So you can really see how this is just after an injection. You can see how this grows with time. So this is a quite useful tool in order to first do some geomechanical estimations and also validate your modelings and your studies with this site measurements from the SLIPENOT project. And this is actually a quite important project because this validates all of this theory about CO2 storage. This project was the one that could prove that this technology is feasible. And we are able to manage and to control how the CO2 will behave in the underground. The second project that I already mentioned is the one located in Iceland. It's called CarbFix. So here they rely heavily on the mineral trapping. And because they rely heavily on mineral trapping, they can forget somehow about the other trapping mechanisms. That means here they have selected the basalt, which has a very high porosity and very high permeability. This is nice because you can easily inject your fluids inside. And the high reactivity will allow you to store the CO2 in mineral form. So it will transform to calcite. You can see this here. This is a core that they drilled from the basalt formation. And the white stuff here is the calcite that has precipitated due to the reaction of CO2 with basalt. And a particular thing here in this site is that because they rely only on mineral trapping, they can just inject dissolved CO2. That means they dissolve first the CO2 in water and then inject on site the water that is separated the CO2. So that means there's no gas. And because there's no gas, you don't have a risk of upward mitigation of CO2 because, as you remember, water saturated with CO2 is heavier than water where there is no CO2, so the water that you will inject will sink down automatically. And this advantage here is that it will consume water. Of course, you have to keep that in mind. And how this works, here is illustrated in a figure on the right. So they mix at the surface water and CO2. They have dissolved CO2 that they just inject on the side. So that the CO2 saturated water will sink down, and on its way it will trap the CO2 in mineral form through calcite that precipitates here. And so this is just a pilot project. It's quite recent, and the injection point is at 540 meters depth only, at 45 degrees. So of course in Iceland you have very favorable conditions because the geothermal gradient is very high, so you have very hot geological layers. They carry out, of course, also monitoring in the site. They inject tracers. They carry out this kind of cores that they analyze afterwards to see how geochemically the dissolved CO2 reacts with the rock in the underground. And what they have seen is that with the drill core analysis that they have 95% of the CO2 that they have injected has transformed into minerals. So what they call here is the instant mineral trapping. So this is a quite nice validation of their new technology that they have proposed here. So with this I will already finish with my talk. So with all my theoretical aspects and also the side projects, I think we can say that underground storage of CO2 is safe. This is what the pilot projects of SLIPENOT and CarbFix has shown. It is safe, and it's actually a lot better to put it in the underground than to leave it in the atmosphere, of course. I've shown you the different physical mechanisms that allow us to trap the CO2 in the underground for long time scales. And with the pilot projects, we know also that the operation is feasible, so we are able to do that. With SLATNA, especially, we have seen that also geophysical monitoring techniques allow us to monitor and to track what is happening with the CO2 in the underground and to react if something dangerous is happening. And there's also some studies that have shown that it's possible to implement the CO2 storage with the regulations in Norway especially, and also in the EU. But of course, politics need to do much more to make the CO2 storage economically effective. With this, I thank you for your attendance.
Different existing CO2 sequestration technologies, comparative study. Well, I'm sure there's many questions I have, but first to the audience.
Concerning the capillary forces, is there any probability that the dissolution of CO2 in the brine promotes the diffusion, the injection?
So you want
by changing the capillary forces?
Yes, sure, it will modify the pressure, and then you have to recalculate your capillary pressure equilibrium. But you can, what it can modify is the contact angle between the rock, because what is an important ingredient in your, I showed you this, if you do some estimations or simulations of your capillary pressure behavior, you need, of course, the structure of the pores, so the diameter, but what's important also is the contact angle between the two fluids and the rock. So this is a property that you need to inject into this model, which depends on which fluids are there and also what is the rock. You can imagine this from the glass bottle. The glass bottle has a certain property that makes the bubble stick there, and this is some kind of property that you need inject into your models and that you need also to measure before. And this can be changed if you change the surface properties of your minerals, for instance. So if you have a dissolution of precipitation, it could be that you modify the surface of your grains, of your rock grains, and that you can modify this behavior.
But for the moment, you have no measurement of that. You have no.
No, I think there was no. Yeah.
Thank you.
You didn't mention the possibility of another target, which would be depleted hydrocarbon reservoirs. Is this something which has been abandoned, or?
No, but it's the same. I haven't mentioned this particularly, but it's the same background.
But the fluid in place has different properties.
Yes, yeah, of course.
Water, so what would be the consequence?
You will reduce the dissolution because there might be some. It depends if your depleted hydrocarbon field, if it's completely empty, if there's no more hydrocarbons or there are some remaining hydrocarbons that are there. If there's a lot of hydrocarbons still there, you will reduce your potential to dissolve the CO2 because it won't interact with the hydrocarbons. And also from your hydrodynamic perspective, it will be more complicated to simulate because you instead of having two-phase flow, you will have triple-phase flow. So.
But you have the advantage of knowing the amount of storage possible.
Yes. Yeah.
Some other question? Yes, Jean.
Thank you, Philipp, for the nice talk. One question: you have shown that there are some new projects starting in the coming years, but how?
Yes.
Yeah. I know that the topic is studied for.
I haven't checked what the topic especially is, or if they. No, I cannot tell if it's just if just other sites, or if they have also they try to do some new technology. I'm not sure.
Yeah, but the topic is studied for more than 25 years, and we see that there are very few projects. Huh?
Yeah, I agree.
And as I know you have looked intensively into the literature, can you explain that?
No, it's very hard to explain, but from my personal perspective, I think the particular politics is still behind it. They don't make it attractive for the industry to invest money in storing CO2. If you would tax, for example, CO2, I think they would invest more into investigating storage sites.
That's exactly the good answer. If you look at the number of projects, there was an increase of number of projects in the years 2000, 2010.
Yes, and then
And after that it decreased, and it started again now. It's because the market wasn't there. So at some point the industrial were going into it, but no money into it. So they stopped. Now they start again. The market is still not there, but it should be there soon. So that's the huge uncertainty now. How do you make it economical?
The surprising thing that the price of CO2 in the market just passed a few months ago, 1 month ago, some $100. And this is the average price of transporting and storage of CO2. And I'm really surprised that if you look at the different scenarios in France, it is not taken into account. So what they call the puits de CO2, the CO2 wells, are just woods and trees, but no underground CO2 storage. I'm surprised.
It's even more surprising that there is a project. Total started in the 2010, I think. They were supposed to store in a depleted gas reservoir at the LAC site for 10 years, pilot. They stopped after 3. Looking regularly in literature, I don't really find any technical reason. This is just political reason. There is, economical aspects of course, but there must also be some political constraints behind too, not only economical. Why did they stop? They don't provide any explanation.
LAC is an onshore field and there's a huge social acceptance issue with onshore. So Total is thinking more and more about offshore fields in France because it's easier in terms of social acceptance.
Okay.
But what's strange about that, because they've stored hydrocarbons there.
It's
So
strange.
it's less dangerous to put CO2 there than.
You're right. It's strange anyway because even in the Parisian basin, there's a lot of gas storage where they inject and they take it out, and it's not as deep as what we target here for CO2, but social acceptance.
There was, please.
Yeah, we had an offshore site near Rotterdam in the Netherlands, and there was an enormous national program of CCS started in 2003, and it finished in 2015. And at that point, there were a whole bunch of companies on the verge of investing, just as a demonstration project, okay? Just waiting for the Netherlands government and a few of the surrounding European countries to invest further in that, to stimulate it, and it fell through. So it was, and ultimately, the governments were not willing to provide sufficient stimulation to get the companies over the barrier. But there was 15 years research done on it, basically. The site was fully characterized. It was an empty gas reservoir. You never know more about it before. And many geomechanical investigations, modeling, hydrological investigations, and it fell through simply because there wasn't the political will to invest to get the companies over the threshold.
This is a really crucial point. Okay, social acceptance has something to do with political decision too. There was a question.
I was just wondering if in the CO2 sequestration, the CO2 cost to do so is taken into account, or is it negligible?
You mean
to get it to the point where it be sequestrated and take action to?
Of course, I didn't talk about this, but it's a very important aspect. You need all the infrastructure. So let's say you have a site that is working here, like the Sleipner, but it's working nicely, but then you have to bring all your CO2 somehow through the North Sea and get it to Sleipner and store it. So depending from where your CO2 comes, you have a lot of cost that is added to the total
The
price.
number of the price of $100 that I mentioned is including transport price.
So the question was about emission of CO2 you have when you do this kind of project?
Yeah, both economically and ecologically.
And it's proven that in terms of cycle, it's positive. Obviously, when you store CO2, the objective is to store CO2, not emit CO2 while storing it. So the overall equation is favorable to CO2 storage results.
What was the question up there?
I just wanted to add on the point of the depleted gas reservoirs and the economy. So when we inject CO2 in depleted gas reservoirs, it depends on the absorption affinity between the hydrocarbon present and the injected CO2. So if CO2 has a higher absorption affinity than the present hydrocarbon, the hydrocarbon tends to dissolve. So CO2 enters the pore, the hydrocarbon dissolves, and there's a system. So we inject with a well and we have a recovery well. So the dissolved hydrocarbon is then taken from the recovery well, and that can use as an energy source and can partially offset the cost of CO2. So this kind of pilot demonstrations has been done in the US through early 200s to.
Well, it's kind of enhanced recovery, but we want to avoid.
Yes,
to
it's
recover
kind
more
of
hydrocarbon.
enhanced recovery. So it can be on, means not except oil, but on gases as well, which are less pollutant, like coal bed methane. So in suppose in countries like India I come from, so there are abundant coal mines. So and coal bed methane is less harmful to the impact. So on those kind of depleted reservoirs, you can inject CO2 and then recover, because it depends on, for example, CPM, the composition is methane. So CO2 has a higher absorption affinity than methane. So this way you can partially offset, but again, monitoring is a huge issue. 3-phase flow means partially saturated with water and 2-phase flow, and so very complex.
Now, I'd like to add some remarks about the project that we don't discuss so much, because mostly we use the injection technology in carbonate type of depleted fields or the aquifers, but the carb field project, I was a little bit interested in it because well, about 10 years ago when I was discussing with the Club CO2 people, they were not really physical chemists at that time, but reservoir engineers, and I was coming more from the geological part and material science part, and I said, well, if you want really mineralization, you need earth alkaline species, and this doesn't exist, neither in carbonates or in sandstones. So you need mafic type of rocks. Okay, but mafic type of rocks are not very porous. So this story here is about basalt. So indeed, providing calcium, magnesium, and iron, and it's porous. But normally the basalts are not permeable. I mean, porosity is close porosity. So this means that this is very fractured.
Yes, and it seems to have. I haven't looked in detail about this, but it seems also you can see that you have huge pores, right?
But they're not connected. They're just bubbles. So there is a lot of porosity, but what do they? I mean, they are kind of startup, so they are selling the product.
I'm also wondering if you inject
a lot because there is a lot of porosity, but most of the porosity is not available. I mean, there is only a fracture network where you can inject really. The growth phase. So of course they try to convince that there is a lot of opportunity. I'm just wanted to mention that all this porosity is not available, only fractures. And then another question. I mean, if they inject the CO2 already dissolved, I mean at some point, the acid fluid will also regress. Dissolve the calcite which is forming itself. I mean, there is certainly some studies to do in the kinetics between the dissolution of the silicates providing the earth alkaline, the precipitation of the calcite, and the back dissolution of calcite due to over acidification, and I think they didn't really do any experimental work on that. They're just aiming at and showing that it's going very fast and it's working, but wanted just to be very careful.
Yeah.
This is kind of we don't know exactly where we go.
But they have shown that they have. No, they didn't put the numbers, right?
Yeah, well, they give a percentage. They indeed for now they pretend it's mineralizing very.
And I'm wondering also because if you inject there and you have a lot of precipitation, you might also clog your.
Yeah, you're causing the porosity, this fracture network, which means that probably then you have to create by hydrofracking new networks and so on. So things may not be that easy. I mean, just to point that this technology, which seems indeed, I mean, on the ground, very attractive, is still on the caution because of many unknown around the technology, and then it should not serve as a pretext to say, okay, let's continue burning CO2 because now we can store it efficiently for millions of years. Because I mean, I read what they say. Okay, basically, that you have volcanic arcs everywhere where you have active plate tectonics and volcanic islands and so on. We can store, and typically they promise that they can store the whole budget that we are supposed to store. But okay, they are startup companies, so we have to take care. Okay, some other question or?
I have the last question. I was wondering what you do at Laboratoire de Mécanique on these topics.
So right now I'm working more on hydrogen storage. So another competitor to take all the reservoirs and use it for another gas. Yeah, but what we're doing is mostly we're doing rock mechanics experiments, mostly on the macro scale, and also some of my colleagues are working on numerical modeling of the rocks, but also the cement that they use for the version. Something that I neglected a little bit in this presentation because the CO2 also interacts a lot with the cement that you put on the sheet, and it can affect the permeability and the stability.
Okay, thank you very much. And interesting rock, not only from the artistic point of view for sculptures, but also for some more basic problems that we are facing. Yes.
Thank you very much for the introduction. I was good because this part of the lecture about the clays is missing in the presentation. I'm not the right guy to talk about the macrostructure clays. In fact, I was just paying attention to the title, and there's a question mark in the title. Underground storage and geoenergies, solution for energy transitions. Yeah, that's it. Oh, I just made it by my mistake. The question mark in the title of the
Clay rocks, yes.
No. The question mark and the title of the conference.
Solution for energy transitions.
Is it by purpose?
Yes, it's on purpose. It's on purpose because we are proud to do what we do, but we are honest enough to admit that we do what we can, and it's probably not the only solution, but it's.
Well, I think they are a part of the solution. Anyway, thank you for this opportunity, and let me say that it's a little stressing to talk about like people that just SPIERS. These guys know everything, so. As I will talk, I will just try to show you some experimental. So the presentation is quite experimental. In fact, it's a course I'm giving on experimental evaluation of thermo-poro-mechanical behavior of rocks, and just I changed the results. I put everything on clays, or clay rocks, clay stones. So this is why I put separately clay rocks. So the half of the presentation is you can transpose it to every rock, every porous rock, and this is like the content probably easier than the older rocks. At the end, I show more research results, but at the beginning, it's really coarse. So it is too easy for you. Please tell me that I will go faster. So I'm a researcher at the Navier Laboratory, and these works are great work in collaboration with Pierre Delage, Philipp BRAUN, who is a master of claystones as well, and some other colleagues. Of course, as mentioned in the previous presentation, one important element in all storage system is the cap rock, and many cap rocks are clay rocks. But here I choose to put an application concerning the underground storage, which is another great application involving clay rocks, and is directly, to my opinion, directly related to the green transition. Even if some people don't like it, but I think it's an important part of the solution for the future. So all of the examples that I will show comes from our collaboration with ANDRA concerning the nuclear waste disposal project in France. So they have an underground laboratory at 500 meters more or less depth, in which since several decades they are doing experiments and we are doing research. So the host rock is a claystone, means that the rock, which an important part which is composed of clay minerals. So here you have more or less half of the water filled by clay mineral, and you have some carbonates, quartz, and some other minerals. Porosity between 13 and 19%. It is extremely low permeability. Depending on who measures the permeability, it's between 10 to the minus 19 to 10 to the minus 21. Anyway, it is very low permeability. It's quite to some extent anisotropic, and have some other numbers. So if you look at the microstructure on the microscope, it seems like this. And so there are many features that we cannot see at this scale. Okay. Again, so for this particular sample, we have more precisely the fractions of the matrix and the porosity. And the rock is very sensitive to water. So if you put it in a glass of water, it simply disappears. And it's a transversely isotropic rock. This is a reconstruction of the microstructure, so we can see that it's very quite at the micro scale is quite heterogeneous with different components of the rock, and we can see them like half models of the microstructure. So you have a clay matrix with inclusions which are of calcite or quartz, and the important part is that you have swelling clays, some swelling clays in the clay minerals, and you have some adsorbed or bonded water around clay minerals, and this makes that the behavior is quite complex and depends, and there are strong interactions with water, with low pressure, with drying, and some complex things in this material. Compared to a sandstone, which is like more regular rock, it seems easier, this one, but this one is already very complex because everything passes through these contacts. So it's quite complex, but it seems at least less complex. But the other one is at the micro scale is a granular, but at much smaller scale, so we have all these complexities plus all the interactions with water and different clay minerals. And of course, it's, as we can see, it's a multi-scale material, but all rocks, most of the rocks are multi-scale. Just this is an example that I have in my course that shows, this is for an Neolithic limestone, shows different scales of the material. This rock is formed by almost 100% calcite, but despite the homogeneity of the mineralogy, it is extremely complex at its microstructure. And we can see the consequences of this on macro scale behavior. So as Chris said, we must look at the microstructure of rocks. This is very, very important. So one nice way to look at the microstructure of the materials, one of the ways is the porosity evaluation. So you have like classical porosity evaluations by drying. In some materials you have a quantity of occluded porosity. And a good way of having an image of the pore size distribution in the rock is by mercury injection. So you can inject mercury progressively by increasing the pressure, and to each pressure you can attribute to a pore size, a pore entry size, and then you suppose that the pores are filled from greater to the smaller, and it permits, of course this is false, but it permits to have like a pore size distribution of the material. This is just an example. I think for a limestone, you have a peak at probably 0.7 micrometer. And I show you the result on color Oxford and claystone from a paper of Pierre Doulage. So you see, this is the mono size. Mostly you have one main pore size at 0.03. The peak is the main pore size. So the total porosity is 17% here. The smallest pore accessible by this method is 7 nanometer, I think 7 or 8 nanometer, depending on the pressure. And so you can see that. So here we are at 13%. So you have 4% porosity with the pores smaller than 7 nanometers in the microstructure of the rock. So now I'll show you some basics of pore-elasticity. Probably you know this, or you're supposed to know this, but anyway, I will show you some basics. But I suppose that you are familiar with the mechanics of solids. So in mechanics of solids, you have like a constitutive law of elasticity. You have a stress-strain relationship. So the stresses are related to the strains by an elasticity tensor. And this elasticity tensor, you need two independent material parameters. You have two different expressions here with lambda parameters or with bulk modulus and shear modulus. You have many choices. And the way that you choose them, sometimes you like these ones or other ones. Or sometimes some theoretical developments are easier by this choice than another choice. Some developments are easier by E and Nu than by K and G. But it's a matter of taste sometimes, or it's a matter of facility of theoretical developments. And okay, most of the rocks are anisotropic, but in the general case of anisotropy, you need 21 material parameters. I think they have never been measured for a given material, but this is like too complex. But the case that is quite common in clay rocks and many sedimentary rocks is the transverse anisotropy. So you have an axis of symmetry here, so like the layered material. And here you have 5 material parameters. So 2 Young moduli, like 2 Young modulus, EH, EZ, and 2 Poisson ratio, and 1 shear modulus. It's more or less easier to evaluate experimentally. But now we should go to the elasticity of fluid saturated porous materials. In fact, in solid mechanics, if you have stresses, you can evaluate the strains, provided that you know the material properties, or if you have the strains, you can calculate the stresses. But if you think as this ball as a volume element, the stresses are not changed, so it's atmospheric pressure, but the volume has changed. So something is missing in this equation. So we need some additional terms as a function of the variations of the pore pressure, the inside pressure, and also the temperature, if you like. But changing the pressure, we can also change the volume of this material. And I will show you, we can take the formula from the book, but I will show you an easy way to derive them, at least for an easy case, and to identify the basic experimental methods to have them. So, some assumptions, in fact. So we consider the porous medium as a sum of a solid phase and a fluid phase. So you have one continuous fluid phase with one pressure. If you have some occluded porosity, it is considered as a part of the solid phase. And the solid phase can be heterogeneous, no problem. And you have one temperature in the whole element. Now, to make things easy, imagine that we are under hydrostatic pressure. So the stress tensor is just given by sigma, which is the mean stress. And so for this material, for this non-porous material, the volume is a function of stress, the mean stress, and temperature. So if I change each of these variables, the volume changes. And in the case of the porous material, the volume is a function of the stress, pore pressure, the pressure which is inside, and the temperature. And the same, the volume of the pores, V and this phi, is a function of the stress, pore pressure, temperature. Okay? From this point, I will introduce an auxiliary variable. For instance, I call it differential pressure, but you know that this is effective pressure. This is the difference between sigma and Pf. And mathematically, I'm allowed to change the variables of this function and to suppose that the volume is a function of the sigma d, which is the differential pressure, Pf and T. Okay? So this is the only assumption that I make for developing the equation. So I just suppose that the volume is a function of these guys. Now, I can do a partial derivative of my volume. So dV, and I divide everything by the volume at initial state. So you have dV over V0 is equal to the variation of V with respect to sigma d when Pf and T constant, the sigma d, and the other terms. So this is just a mathematical partial derivation. And I will give names to these guys in colors. So I call this -1 over Kd, I call this -1 over Ks, and I call this alpha T. And so I just invented a constitutive law for a porous material under isotropic stress. So you have three material parameters. So you have, this is the volumetric strain, one material parameter Kd, one material parameter Ks, and another material parameter alpha T. And so we need to know how to evaluate them. In fact, we need an apparatus which is called the triaxial cell. So in this apparatus, in which we put a sample in a membrane connected to tubes, connected to a pump. And so in this apparatus, we can individually control sigma, the confining pressure, T, the temperature, you can heat the cell or cool the cell, and we can control the pore pressure, but at the ends of the sample. So in my equation, I can individually control the variables of my equation. So for measuring the Kd, it was the mathematical definition. I need to change the sigma d in a way that Pf and T are constant. Okay? So I should do an isothermal experiment, so I keep the temperature constant. I keep the pore pressure constant, and I vary sigma. In this way, sigma d is varied, Pf is constant. Okay? And I measure the variations of the volume, and the variations of the volume with respect to the variations of the stress can give me the Kd, which is called the drained bulk modulus. And this is called a drained isotropic compression test. Okay? So pay attention that the word drained is associated with this thing. Okay? Drained means that there is no noticeable pore pressure variation. Then the other coefficient was Ks. For this coefficient, I should vary Pf in a way that sigma d and T are constant. So the test is isothermal, but to keep constant sigma d and to vary Pf, I need to change sigma and Pf in the same way. So I apply a simultaneous change of confining pressure and pore pressure. In this way, the differential pressure remains constant, and the volume variations of the sample gives the modulus Ks. And this is called an unjacketed compression test. I will explain later why. And the third test is easy, is a drained heating test. So I need to change the temperature by keeping the stress and pore pressure constant. And then I measure the volume, the variations of the volume, and have this third parameter, which is a drained thermal expansion coefficient. Okay? Once again, I call it drained because dPf is equal to 0. So in a triaxial cell, generally you can measure the strains with the strain gauge. And you can independently, of course, change the confining pressure and an axial stress. So the sigma is the mean stress, and the volumetric strain is normally axial strain plus 2 times the radial strain. Then from this point we can introduce the effective stress concept, because we have, or epsilon, the strain which is function of the differential pressure and pore pressure. We can just introduce this thing here and rearrange the equation in this way. Okay? Then I will call the thing in this parenthesis B. So I call, cannot see the light, the red point. There is no red trees. Okay. I will call this guy B. So this is the bioeffective stress coefficient. And so I have a definition of kind of effective stress, which is called, this is equal to T sigma minus B dPF. In fact, the interesting thing is that the epsilon was a function of stress and pore pressure. Now is only a function of sigma prime. So we can find the same equations that we had in solid mechanics. And it is interesting because it permits us to use like a solid mechanics software or solid mechanics analytical solutions for a problem of related to a porous material by using the effective stress. So this is called. And in a particular case of soils, you have the Ks of many rock minerals are between 40 and 60 gigapascal, and for the rocks, the Kd is quite small. So B is very close to 1. So in this case, the bioeffective stress is reduced to Terzaghi effective stress. So this is why in the soil mechanics course, everything is a function of the Terzaghi effective stress. This is due to the assumption related to the incompressibility of the solid grains. Then this can be extended like to the general, because the derivation was for isotropic stress, but this can be extended to the general stress relations, in which you have two more material parameters. So you have effective stress coefficient B and the volumetric thermal expansion coefficient alpha T. And of course, once again, we can rewrite this equation to find again exactly the form that I showed you in the first page, which is the form of solid mechanics by using the bioeffective stress instead of the total stress. And now you need to trust me. We can develop in exactly the same manner by writing the partial derivation of the variations of the pore volume. We can find this relation for the porosity variations, but I just skip the derivation. So you need two more material parameters. So the variations of the porosity here is a Lagrangian porosity. So it is with respect to a fixed total volume. So it depends on B, depends on bioskeleton modulus N, and another parameter Q, which has no particular name, if you have any suggestion. So you need two more parameters here for porosity variations. And in the transverse isotropic case, which is more adapted to many clay rocks, you have two B coefficients and two alpha coefficients for horizontal and vertical directions. Now we should introduce also the drainage concept, because in all these experiments I told that we keep the pore pressure constant, but keeping the pore pressure constant is not that easy, is not an easy task, because we can control quite easily the confining pressure and the temperature more or less, because temperature diffusion is quite quick, but the pore pressure we can control it at both ends of the sample, and in some cells at one end of the sample, but we cannot really control its diffusion. So to demonstrate this, imagine a porous material with an initial state. You have an initial state of stress, an initial state of pore pressure, and we take the strains equal to 0. Like you go to the kitchen, and after washing the dishes, take the sponge, you put it on the table. So you have a porous material, saturated porous material with an initial state, and then in the instance T0 plus, so instantaneously, you put a weight on it. So you look for a big rock mechanics book, and you put it in the sponge. At this first instance, you have an instantaneous stress increase. Of course, with very velocity. You have an instantaneous pore pressure increase. Okay, you have some strain, but at this time, because we are talking about just one moment, the water have no time to go out of the sample. Okay, the instance that you put the weight, the fluid mass in the sample does not change, but you have the pore pressure increase. Then, if you wait a little bit, water flows out of the medium, of the sponge, and then you have the stress remains the same. A part of this excess pore pressure is dissipated, and you have some more strain. Okay? And if you stay sufficiently long, and this sufficiently long can be 5 minutes, it can be 15 years, depending on the material, the pore pressure goes back more or less to its initial state. The strain goes to a final state. This is the final state of the material. So, and this happens irrespective of the load and irrespective of the permeability of the material. Every time you put a load, this happens. So, this final state, we call it the drain condition. So, the drain condition, we apply the load, and there is no pore pressure increase. This is the drain condition. The first state is the undrained condition. We apply the load, there is no change in the fluid mass. Okay? And of course you have a pore pressure increase. And this intermediate state is called the transient condition, or in soil mechanics books we call it consolidation. And we will see later that we design experiments exactly based on this concept. Now, just to imagine that. So I told you that this happens irrespective of the permeability and of the load. Instead of putting the book in a book, a theory book, and I put it page by page, okay, with this velocity, what happens? Any guess? Of course, the same thing happens. When you put the book as a book, you have a big pore pressure increase, and then you have a decay. Okay. When you put it page by page, you have a short increase and then decay. But if it's not still ended the decay, you have another, and another, and another, and another. So you have this thing. But if you look at it from quite far, it's not the pore pressure is not changing. In fact, you just applied a drain loading. You applied the loading sufficiently slowly in a way that the pore pressure increase is not that much. You have always a pore pressure increase, but it does not affect the strains, in fact. And this you can tell that, yeah, I did a drain loading. Okay? And this is exactly what we are doing in the experiments. We try, depending on the permeability of the material, apply the loads sufficiently slowly in a way that the pore pressure changes are not important. Okay? So, globally, sometimes some tests we control the pore pressure. So here is drained, pore pressure equal to 0. But we can control it, apply a pore pressure variation that we want. And otherwise, we close the valves of the drainage system, and we call it an undrained experiment. So we don't let water go out of the sample. So we mimic the first condition in which the water cannot go out. These are the two main loading conditions, but we will see that we can just have any condition in between. So then we can simplify this. So you have already seen this. In the drain condition, in the drain experiment, drain isotropic compression test, you change the confining pressure with constant pore pressure temperature, and the measured variables are the three strains and the fluid volume. So you already saw this, and if I simplify this equation by dpf and dt equal to 0, I have dphi, because by the variations of the fluid volume coming to the pump, I can evaluate the variations of the porosity. And the variations of the pore volume divided by the total volume gives the bioeffective stress coefficient. So it's another way of visualizing the bioeffective stress coefficient in a drain loading is the ratio of the pore volume variation to the total volume variation. In fact, in the soil, when the grains are incompressible, the whole total volume variations comes from the rearrangement of the grains. So these two are equal. But like in the sandstone, a part of it comes from the compression of the grains. So this is why they are different. And this is the unjacketed test, so the measured variable is Ks. Measuring the fluid volume in this experiment is very difficult because the fluid, you have a volume of the fluid in the pump which compresses, and so you have great errors. It's normally not possible to do anything interesting with the fluid volume in this experiment. And in the unjacketed compression test, in fact, as we mentioned, we apply the same pressure as confining pressure and pore pressure. So if you consider an ideal porous material with a homogeneous solid phase, so this is like idealization, in fact the measured Ks is equal to the bulk modulus of the mineral. Okay, if you have a limestone, and if you do a good experiment, normally you should find the Ks of something around 65 gigapascal, which is the bulk modulus of the calcite. Or if you do it on a sandstone, you should measure something around 43 or 38 gigapascal, which is the bulk modulus of the quartz. And in this case, the parameter n, the biomodulus, is given by this expression. So you need one less parameter, in fact. But when you have a heterogeneous solid phase, like Cox claystone, the Ks is bounded between the bulk moduli of different minerals. Okay, you will be some weighted average. We don't know exactly what, but something between the bulk moduli of the minerals. And then you have the heating test, which gives the alpha D. Normally, if we can correct the fluid volume variations, we can measure the Q. But here also we have big errors on the fluid volume, particularly because you hit the cell, but normally you don't hit the pumps. Sometimes you can, but normally you don't hit the pumps. And so to correct this thing is quite difficult. And in an ideal porous material, the drain thermal expansion coefficient is equal to the thermal expansion coefficient of the mineral. So you can just find it in the book. And the parameter Q is given by this relation. So in this case, in an ideal porous material, in fact, you need just two parameters. You need the alpha D and the D. And the others you can just evaluate from these theoretical equations. But in a heterogeneous solid, the alpha is quite complex. It's a function of the thermal expansion of different minerals, but also function of their mechanical rigidity. So, because due to the thermoelastic interactions. So it's quite complex. And you need to measure it. And you can have another test. For example, I'll give an example of pore pressure loading test. In this set, you keep the confining pressure constant, and you increase the pore pressure, you decrease the pore pressure. And so here we need to put d sigma equal to 0, and you will see that d epsilon is equal to minus b over kd d sigma. So we measure another parameter is a biomodulus, and which is equal to 1 over kd minus 1 over ks. So you have different ways of measuring the combinations of different parameters. And also, you can also do the experiment, design the experiments in which you change pore pressure and confining pressure in different manners, with different slopes, and then you have always some combination of the parameters. And for the undrained condition, in fact, as I told, the theoretical definition is the fluid mass constant. So the fluid mass is given by the fluid density multiplied by the porosity. So its variation is given by this. So it's a function of porosity variation and fluid density variation. So here you need another ingredient, which is the constitutive law or behavioral law of the fluid. And this is this thing. So the variations of the fluid density is given by this equation as a function of the fluid compression modulus and fluid thermal expansion coefficient. And by using d phi as this equation and the absolute equation, we can rearrange the equation and find these two equations. So at undrained conditions, the pore pressure variation is given by the mean stress variation as a function of the Scampton coefficient and temperature variation as a function of the thermal pressurization coefficient. And in a similar way, you can define an undrained bulk modulus and an undrained thermal expansion coefficient. So you can see here that if we load the material in undrained condition, the pore pressure increases, and if we heat a material in undrained conditions, the pore pressure increases. Can you give me an example of undrained heating? Yes, okay, nuclear, it's complex. But I was looking for some easier, some simpler. Okay, this video comes from Mr. BRAUN. If you put these things in the microwave, don't do it at home, but in fact, the tomato is an excellent example of undrained condition because you have a saturated porous material, you have solid, you have fluid, and the skin is quite impervious. So when you heat a tomato, in fact, the physics behind this is that you will see from the equations, most fluids have a thermal expansion coefficient more than 10 times bigger than the solids. So you have a mixture of fluid and solid, you heat, and so the fluid wants to expand 10 times more than the solid, and it cannot go out. So it pressurizes, and at some point, the pore pressure passes the sigma theta theta over the skin and the traction resistance, and okay. But this is very important, for example, in nuclear waste disposal, because the permeability of the medium is very low. So when the heating happens, the material have no time to dissipate the pore fluid. And also you have it, for example, during the seismic sleeps. John has very nice work on this. During seismic sleep, you have a pore pressure increase due to shear heating. So because the fault zones are normally of very low permeability, so shear heating causes an increase of the pore pressure, and it decreases the normal effective stress on the fault, and it accelerates the sliding of the fault. So the phenomenon can be quite important in many, many applications. And so the behavioral law of water, you have the alpha, the thermal expansion of water, it has a quite important dependency on temperature. Its compression modulus has some temperature dependency, but less important. So it should be taken into account. And then you can find relations between the undrained parameters and the drained one, because undrained parameters are not real parameters, just they are boundary condition problems. So the Scampton coefficient can be written as a function of different other parameters. It's bounded between 0 and 1. And the undrained bulk modulus also can be written as a function of the drained bulk modulus, Scampton coefficient, and U coefficient. And you can see that the Ku is bigger than Kd. In fact, compressing a material in undrained condition is more difficult because you should need to compress the skeleton and water. The same thing for thermal pressurization. The thermal pressurization coefficient, you can calculate it if you know other material parameters. And you have the undrained thermal expansion coefficient is bigger than the drained one because you drain the whole system in which water expands more than solid, so the whole system expands more than compared to its drained condition. And okay, so for ideal porous materials, you have like different expressions of the same parameters. And if you take this case of the solids, you have Ks much bigger than Kd and Kf much bigger than Kd. In this case, the Skeleton coefficient is equal to 1, and the Ku tends to infinity. So in soil mechanics books, it is written that the soils are incompressible at undrained conditions. Okay. So you know that this is an approximation. Then we can write all equations in transient condition. So we can have these two forms which are interesting. This one, so we can generate the pore pressure by increasing the stress, increasing the temperature, and then you can dissipate it as a function of the permeability of the material, the viscosity of the fluid, and this storage coefficient, which depends on these parameters. This is another form, just the stress is replaced by the strain. And of course, so these are this set of coupled equations. When you run the software with for a coupled problem, like you run Praxis or Abacus for a coupled problem, in fact, you are solving together these two equations. So the first one is the equilibrium equation, in which the stress is replaced by this form, and this is the fluid mass conservation equation. So a coupled, this forms a coupled system of equations, which is not solved in softwares by finite element. And this can be extended to the presence of non-elastic strains. So when I say non-elastic, that can be plastic, that can be viscoelastic or viscoplastic, that can be from chemical origins, that can be from everything which is non-elastic. So we suppose that epsilon is a sum of epsilon elastic versus non-elastic. And so you have a part of non-elastic porosity change here. And normally, most of the time we can consider that the solid phase remains elastic. It's not a very bad assumption. So the non-elastic porosity variations are simply equal to the non-elastic strains. At undrained condition, here you can see that, for example, you have an additional term for pore pressure generation. So when you have a contractant non-elastic strains, when you have a contractant plasticity, dphi is smaller than 0, so you have excess pore pressure generation. Otherwise, if you have a dilatant material, you will have a pore pressure decrease due to plasticity. So these questions in transient conditions. Now we go to the experimental evaluation. So we go to the experiments. So normally we use triaxial cells, as I showed you already. So this cell is a simpler cell that in which we are doing only isotropic experiments. So you have a small sample. There is a membrane which is covering the whole sample. On the sample you have a strain gauges, and then you have a heating system around the cell. This is a more conventional triaxial cell in which you can control the axial stress and the radial and the confining pressure. This is the appearance of the cell. So you need to pay attention to the conservation of the blocks, then the samples need to be cutted. Okay. Normally we use length to diameter ratio of between 1.5 and 2.5. 2 is a good number. It is important to prepare parallel faces to not have errors in the experiments, and also to lubricate the faces. You could see this morning from the sample of Noah. And then these are different steps of putting the sample in a triaxial cell. The things are a little more complex for clay rocks. These are clay stones. So the clay stones after the coring are kept in like specialized cells in which they are protected to prevent the humidity loss. And there is a spring which puts some pressure on the sample to prevent the swelling. And then we should cut and core them in dry conditions. And normally we keep them in bags under vacuum. Then, as I mentioned, for the example that we put the book page by page, we need to determine what is the good loading rate to ensure the drainage conditions. Because you can always load infinitely slow, but each experiment will take 3 or 4 months and you don't have time to do everything. So you should need to find some optimized things. And Philipp did during his thesis a very nice theoretical analysis by using this diffusion equation, the transient equation, to evaluate the pore pressure and the strains at the center of a sample, which is loaded by a given rate. Okay? I will not enter into the derivation. I cannot do it. So you have everything, the pore pressure and the strain, which are functions of two functions, f1 and f2, which has these forms. Okay? So once you know your material property, or once you have some guesses of your material properties, you can have a prediction of the pore pressure and the strains inside your sample. And for example, and we can do just numerical tests. So this is a loading-unloading cycle, okay, on a given material by two different loading rates. So 0.57 kilopascal per minute or 1.14 kilo, so double the first rate. So we are doing a loading-unloading, okay? And at the right side, you see the excess pore pressure inside the sample, at the middle of the sample as a function of time. Of course, when you load more quickly, you have more excess pore pressure. Okay? And if you look at the stress strain curve from this experiment, in fact, this is a purely elastic material. So if you are doing it like with perfectly Pf equal to 0, you will have just a line like this. Okay? But you have a nice hysteresis loop here, and if I tell you nothing, you will think that your material is viscous. It's like a creeping material. But this is just a pore pressure equilibrium problem. So sometimes we find this kind of response in material. Of course, if you are doing it in a cell, it's sure that it's creep. But when you are obtaining such a response on a low permeability rock, it's not sure that it is creep or if it's just a diffusion of the pore pressure. And if the material is creeping, distinguishing these two is quite challenging. So it is possible to define a kind of error between the real property and the measured, the real property corresponding to an infinitely slow load, and a real property measured by a given load. And here Philipp did an example that he fixed some error of 1% error. We can admit 1% error, and so we can find the dimensionless time permitting to have this error. Okay, and you can see that here you can apply a quicker load for a drain compression test than a drain heating test. So you cannot apply, or for example at 2 mechanical, for an unjacketed test, you need to apply a slower rate with respect compared to a drain test. Okay, so in this way, by fixing an error, and of course you need some idea of the parameter, but you can optimize the loading rate of different experiments. Another thing is that the undrained condition is theoretically defined as a condition which is no variations of the fluid mass inside the sample. But in fact, in the cell, your sample is connected to the tubes, and you close the walls at the exterior. So you can have some mass exchange between the sample and the tubes, and the tubes can expand also. So you have the fluid mass exchange between the sample and the drainage system, and the compressibility of the drainage system. And this induces errors in the measured parameters. And so before Bishop proposed something to correct the Scampton coefficient. And then with Jean, we proposed a similar thing to correct the measured thermal pressurization coefficient. So of course you need some calibration of your experimental device, but this can be quite important, and we will see real examples. But here just a parametric study. Globally, the volume of the drainage system that should be as small as possible and as rigid as possible. Globally this thing, but you can have errors like 50% error in some parameters. So that can be quite important errors depending on the different material properties. Of course, it depends on the material properties as well. So then, despite all the precaution on coring and preparing the samples, we have always some drying of the claystone samples. So we need to resaturate them because these material properties are highly dependent on the saturation. So we need to resaturate the samples before the experiments. Because if you saturate, and this resaturation, we think that it should be done under the same mean stress as the in situ conditions, because otherwise the sample will dilate and will be damaged. So in our procedure, we put first the confining pressure equal to the more or less the in situ stress on the sample, and then increase the pore pressure up to the in situ value. And we wait sufficiently to have a stable strain or a stable pore pressure injection volume on the sample. And then normally it takes 1 week, and then we consider that the sample is saturated or saturated enough. So here I show you some examples. So for this case, we had 2 samples, one quite well saturated, another one not that saturated. And so we first saturated the sample. So the initial conditions of the sample is 12 megapascal stress, 4 megapascal pore pressure. And then we increase, so we have 2 different tests here, in fact. So we do a drained experiments. So we unload the sample, unload, reload. So this is elastic, it will remain elastic. So we do a drained experiment. And then we do a pore pressure change. We keep the confining pressure constant, we increase the pore pressure and decrease the pore pressure. And then we do an undrained, unloading, reloading. Always go back to the same point. And at the end of one sample, we do an unjacketed compression test. Okay? Okay? We can somehow criticize the fact of performing several experiments on the same sample, but at least you will have a compatible, more or less compatible set of results, because you have sometimes quite important variability of samples from one to another. So in this way, you have more chance to have a compatible set of parameters. So the unjacketed test. So we have a 2 megapascal confining pressure change. So what is interesting is that the response is quite anisotropic, because the rock is anisotropic. So you have the axial strain, which is quite higher than the radial strain. But if we forget this, like we take the volumetric strain, we will see, I will show you later how we analyze these things. But if we forget that it is anisotropic, if we take just an average behavior, isotropic behavior, we have a Ks of 21 gigapascal. Okay? And this is quite an important value to put in the calculations. There are not many people who measure this kind of parameters. And then this is the isotropic compression test. So again, you have an isotropic response, similar, and you can have a KD of more or less 3 gigapascal. And I define just these variables. D1 is the confining pressure divided by the axial strain, and confining pressure divided by radial strain, like 2 different moduli. And you have the pore pressure loading test, which permits to measure the parameter H equal to 3.47 gigapascal, and with 2 different variants corresponding to axial and radial strains. So at every experiment, we can see quite important anisotropy of the response of the material. Then you have undrained isotropic compression. So you have the measured Skempton coefficient equal to 0.63, and you have the measured undrained bulk meters equal to 7 gigapascal, again anisotropic. And when we correct them, it's quite important. The corrected V is equal to 0.84, and the corrected Ku is almost doubled. So here in this particular case, the corrections are very important. Then we have a set of parameters. In fact, we need only 2 or 3 parameters, but we have an overestimated set of parameters, but we can do a compatibility test to see if the experiments are compatible between each other. So, for example, you have Ks can be determined as a function of Kd and H. Okay? So you have Ks directly from Kd from test 1 and test 2, you have them here, H from test 1 and test 2, and you can evaluate the Ks by the equation. The values are very close to the directly measured Ks, which comes from, this is from drained experiment, pore pressure loading experiment, and this is the unjacketed experiment. So it's quite interesting. And we have many different ways of calculation of the bioeffective stress coefficient by combining different parameters. So this is a combination of drained and pore pressure loading, drained unjacketed, drained undrained, undrained pore pressure loading. So by combining different experiments, you can have different ways of calculation of B. And all these give quite close values with an average of 0.87 or 0.9 more or less. And shows this, that gives confidence to the results. You have a compatible set of parameters. But then we can try to just analyze to some extent the anisotropy of the material. So we have here the drained experiment and the pore pressure loading experiments. By playing a little bit with the theoretical relations, we can find these 2 expressions for BH and BZ, the 2 bioeffective stress coefficient as a function of HZ, the 2 H coefficients, the 2 D coefficients, and 1 Poisson ratio. Okay? So this Poisson ratio, we don't have it, or anyway, we didn't measure it for this particular sample. But we were lucky because looking at the equations, the results have a quite weak dependency on the Skempton coefficient. If I change the Poisson ratio from 0.2 to 0.35, for example, the BZ varies from 0.82 to 0.85. So the results are not that sensitive to this Poisson ratio, so we can, and then we have an estimation of this parameter, of course. We can have the values of B, the two bioeffective stress coefficients by this way. And then going to the drained heating test, the things become much more complex. In fact, of course, the result is anisotropic, but if you look even at the volumetric strain, here we hit the sample. So we hit the sample. At the beginning, the sample dilates, like any other material, but at some point, it starts to contract. So we are heating the sample and it contracts. So it's a kind of, we call it like a heating compaction or a heating collapse or a thermal collapse. It's a kind of plasticity. It's a kind of softening mechanism of the plasticity which makes the sample contract due to heat. But as if the things are not sufficiently complex, if you look at the result of the experiment, so here the heating path, in fact the sample is creeping under isotropic stress. So here the temperature is constant for almost 20 days, okay, and the sample is creeping. And then we have our drained heating test here, okay, and then the temperature is constant at 80 degrees and the sample is creeping. Creeping, I don't know, there's a time dependent thing. And in fact, during the saturation, the things were not stabilized, they're straight. So at some point you think that there is really creep because there was enough water to saturate the sample. So if you look at the creep, of course this is much more important at 80 degrees than 25 degrees, and it is again anisotropic. So the fact that the sample is creeping, I cannot use these results to evaluate, for example, the alpha D, the thermal expansion coefficient, because there are some artifacts. There are some errors due to the creep. So I need to separate the creep. So what we can do, I need to make an assumption. I assume that the creep is given by a kind of Kelvin law. Okay, this is the model with these parameters. So because this is going to a kind of stabilization, I choose this model. So you have two parameters, a K and a neta. And we filled them separately for 25 degree and 80 degree. Even if these are the continuity of the same experiment, we did as if they were separate experiments. That's not totally true. So we have an idea of the parameters. And then we assumed a temperature dependent equation for K and for eta. And in this way we can simulate the whole creep procedure during the experiment, including the temperature variations here. Now I can separate the creep from the strains that I have here. So the red one is the result with creep, and the green one is the result without the creep. So here, the impact on the parameters is quite important. So here we can have the drain thermal expansion coefficient here, and this is a kind of elastoplastic coefficient which can be used for fitting the head. And then we need also for this material to evaluate the permeability. So when the material is of high permeability, we are using steady-state methods. And for low permeability material, we need to use transient methods. And in transient methods, you have plenty of them. You need to generate a pore pressure gradient in the sample, and then you release the pore pressure at a point, and you follow the evolutions of the sample. And then you need to back analyze the whole thing and to evaluate your permeability. Sometimes there are very interesting methods. I'm thinking of one method which is called beam bending, proposed by George Scherer at Princeton. You take a beam of the material, this is used for concrete, and you deflect it. And the deflection creates compression at the upper side. If I deflect it like that, you create compression at the upper side and traction at the lower side. So at the upper side, you have a pore pressure increase and the pore pressure decrease at the under. So you create a flow of water, and due to this flow, the deflection goes a little back. And by following the kinetics of this deflection, you can feed the permeability. So we have many experiments like this. You can heat the sample instantaneously and then let it cool. Okay, the method that some years ago I proposed, I presented because that we make an introduction for another method that we applied to clay stones. In fact, I put the sample into axial cell and I apply an on-drain loading. For example, I apply 50 megapascal confinement pressure. And so it generates a pore pressure, like 30 megapascal pore pressure. And then I release the pore pressure at the top of the sample and fix a pore pressure equal to like 1 megapascal. So you have a pore pressure of 30 and 1 here, so the water starts to flow out of the sample. And this flow causes a progressive reduction of pore pressure I can measure here, and also a progressive contraction of the sample that I can measure by these radial LVDTs. And then I can do a reverse analysis of the whole system to back analyze my permeability. And the interesting thing is that it gives access to permeability over a large span of the confinement pressure. So that was one result. That was on a hardened cement paste. In fact, that was not a clay stone. So this is the pore pressure decay, and this is the radial strain. And the bad thing is that even if the pore pressure is more or less constant at the end, the sample continues to contract. So the sample is creeping, in fact. So this is a bad thing. So I can model the whole thing with this transient equation that I showed you before, including the non-elastic porosity changes. And I suppose once again a Kelvin model for the non-elastic part of the thing. And also because the porosity changes quite a bit during the experiment and not in a homogeneous way, the porosity will be lower at the top of the sample because there is no compaction. I suppose also a porosity law for the permeability. And then you can fit the whole thing. So in one experiment, I can fit a permeability porosity law for the compaction of my material and also some creep parameters. And then, inspired by this method, Philipp proposed a more complex thing. This is very interesting because the previous studies are quite long. So in a thesis, we can do just like 4 or 5 experiments and that's it. So you have some dispersed points on the curves. And we wanted to have like more results. So this method, in fact, we put a sample, take a sample. We apply a quick loading, a very quick loading. That can be a mechanical or thermal loading. So you apply a loading quickly, you read the sample quickly. So you measure some variation of the volumetric strain, and at the beginning probably you measure no pore pressure change, because the pore pressure measurement needs some fluid mass exchange between the sample and the pore pressure sensor. And if you go fast, even there is no time for this. But the strains are immediate. So you can, the strain variations are immediately affected, but not the pore pressure change. So for example, in a mechanical loading, the initial slope gives directly the Ku or alpha U directly. There is no need to correction because this is just the right value. And then when it stabilizes, you have the measured value which contains errors. And the pore pressure change gives the value of B or lambda, the thermal pressurization coefficient. And then you release the pore pressure in one point, and you let the pore pressure dissipate. And from this dissipation, you can evaluate the permeability by the same method as previous. And when all pore pressure is dissipated, this thing gives you the parameter H, and this thing gives you KD and alpha. So you can, and the experiment is quite fast, like 24 hours, and you can measure 5 parameters in a quite fast way. So it changed our way of producing results. You will see. So these are 2 examples. This is a mechanical test. So you have an instantaneous confining pressure increase. So this is the pore pressure response, the red one, and this is the measure the strain. So you have the Ku at the beginning and Kd at the end. And so you have the 5 parameters evaluated in this experiment. And this is an example of the thermal loading. So you have a quick thermal loading and a dissipation. And these are the parameters measured in this experiment. And there are 2 common parameters, H and permeability. And you can see that they are quite close in 2 experiments and shows the good quality of the tests. Okay, so this is the quality of permeability filling. In fact, it's quite good filling. So from this, we could have many results which permitted to fit the stress dependency of the bulk modulus of this material with a kind of exponential law, and also have some stress dependency of the bioeffective stress coefficient. And as Philipp had many results, he did, but in this point you should believe him. He did a quite general regression analysis on the whole results to minimize the parameters, like he just. And in this way we can have almost all parameters, so we can have the vertical and horizontal Young modulus, and with some comparison with the existing data. Of course, the errors are sometimes big in this kind of approach. But anyway, you have some values that you can use. So you have the Poisson ratios, you have the Biot coefficients, which are quite close. In fact, it is very interesting and intriguing. I cannot explain this. When you look at the stress strain behaviors, the material is quite anisotropic. The axial strain is quite different from the radial strain, but the 2 Biot coefficients are quite close. In the previous study and this study, there's not that much of anisotropy in bioeffective stress coefficient, but the Scampton coefficients are quite different. One much bigger than one, and another one smaller than one. Okay, I think that's it. Some differences if you want to read more about this. Thank you very much.
Yes, thank you very much for this outlook on the complexity of porous media with very low permeability, which complicates quite a bit the mechanical perspective. Some questions?
Difficult question will be for Philipp. So don't hesitate. Transfer them.
Very important, a very simple question. Can we store nuclear waste?
You want my personal opinion, like as a person.
Yes.
I'm not speaking as a person of École Polytechnique, as myself. I feel like I'm able to buy a house at Blue.
Yeah.
I'm confident in the system. I think it will work. It will work. In fact, you know, there is almost every research lab in France is working on this since 3 decades. If we cannot do this, I will be really disappointed from the science.
No, I mean
This is my just personal opinion.
No, I understand. Actually, you need this cap rocks, okay, so life over tens of millions.
Yeah, they're working.
To protect different kind of reservoirs, so for sure, sea properties are really extraordinary. And no, maybe more questions.
Yeah, there is a process.
Yeah.
So I have some more question. I find you research the center class drawing and under the drawing condition, but the water will influence the structure of the pore structure of the soil. I don't.
Sorry, can you repeat the question?
I mean, you research the permeability of the clay soil.
Yes.
But the water will influence the pore structure of the clay soil when you do the experiment. If you inject the water several times, then the permeability will change.
No. The water is harmful if you remove the confining pressure. But you know the material in the nature is fully saturated.
Oh.
So water is not basically harmful for this material. You activate the dilation mechanisms when you remove the stress. So you permit the clay layers to expand. But when you have the confining pressure, the water is not harmful. This guy is living with water. This is always saturated.
If I can you provide us some insight on the effect and the impact of the heterogeneity of this kind of rock towards the measurement you do? What's behind that is that compared to more classical rocks such as sandstone carbonate that can be heterogeneous and that have some impact on the geomechanical properties, do you think that for claystone the impact is stronger or less?
You think about the spatial heterogeneity of the
if you have I don't know, some layering into your sample. Because
yeah.
The deposit environment is quite complex.
There is a spatial heterogeneity of the material. I cannot give you numbers, but I know that Andra is studying this quite seriously. I cannot give you numbers from my experiments because I didn't sufficiently study different. Because for the experiments, because we need to have one challenge is to have just one set of compatible parameters. You see, these are. It may seem simple, but they are really challenging. You know, for years, the people were using a biocoefficient of 0.6. Somebody decided that measured that was 0.6, and for years in every and even still you can see publications with 0.6, but we measured several times. It's more 0.9 than 0.6. It's not. The people were not used to test these rocks. They started just by breaking them like a piece of granite, a piece of basalt. But this is much more complex. You need to really pay attention to the saturation, to the elevation, everything. And for this reason, we try to have more or less the same from the same unit to have a compatible set of results. At least we can do the numerical, because these results are then injected. I couldn't show everything, but we use these to develop constitutive laws, and then we are doing numerical simulation at the structure state. And for this, we first need a compatible set of parameters that we can inject in the simulations to have the results, and then the spatial variabilities around us. So this is why I don't have a broad vision of the problem.
about the heterogeneity, not exactly the heterogeneity, but the variation in the chemical composition. That is to say, the type of clay. So, for example, okay, the smectite is progressively turning to iodide with potassium replacing. Yeah, well, it's kind of natural transformation process, replacing sodium, for example, by potassium, which make then the clay much less swelling. And okay, so the ANRA type, the bio type of clay has limited amount of swelling clay, smectite, and other formations are very variable. I mean, like the carbonates that present everywhere differences, microstructural differences, and the different clays are very variable in terms of chemical composition of the clays and therefore the swelling.
But it happens during a long time.
Yeah, this happens for a long time. Well, except if you have, okay, for example, some tunneling and some fluiding and fast exchange of fluids. So, for the purpose of storage, okay, you will have concrete. Then there will be exchange with alkalis from the concrete, and this will affect necessarily the chemical composition of the clay. Then potassium, for instance, and therefore turning the smectite to iodide and solidifying really substantially the swelling properties.
I didn't know that, but it seems interesting. If you can transform smectite to iodide, it can be a good thing for the material. But I'm not familiar.
No, it's kind of remark to
it's
go further.
It's very interesting. Because anyway, for the construction phase, I think they need to do with the material at its initial state. Of course, it is different for each site. In Switzerland, it's a different composition than in France. But I didn't aware of this variation with time.
Yeah, well, this is why the ANRA has different departments, of course. So chemistry departments and mechanics departments, and okay, they try to get all this together, but the material is so complex, so reactive that okay.
This is vast and beautiful.
Vast.
It's as you told in the beginning, that was very good as one of the most complex rocks that exist. I know one more complex rock, which is not a rock, which is the cement paste. This clay is a little more complex because it's varying with time, but yeah, it's quite complex. Yes.
Some more questions?
Yeah, one more question. I'm quite impressed because these measurements are really difficult, and furthermore on clay, because I think the stability of clay over time when you store it is a real big challenge. And so my question is, how do you ensure that your clay, when you core it and when you store it in your lab before your measurement, stays the same and is not altered by the storage?
Andra made really big progress on this. Normally, I think the samples are put in the cells, I think, within 1 or 2 hours after coring. So they really minimize this, and we can see this from the saturation degree of the samples that we receive. I think now we are more than 90% saturation when we receive samples. And this is substantially changed in a few years. So they are really.
How much water this makes in weight percent? It's around 6-7.
Yeah,
6-7%.
That was in the first slide. Yeah, that should be the same.
But the point is that these cells where they store the cores, they apply the load, the spring load, always in the same direction, independently the direction of drilling with respect to the stratification, whether they drill horizontally or vertically.
Okay, I see.
Always in the same direction. So
okay, I see.
This load, which is preload, supposed to prevent opening of microplastics.
Okay, if it's other side, it's in the outside.
Sometimes, well, it is applied within the stratification. And what we did last time we worked with ANRA is to systematically scan, microtomograph the samples in order to select specifically those which present the less possible
But is there a better way than cells? I don't know all the options. Is there a better way than these cells?
Well, they don't have another. No, this is a good option. The
We
point
should
is that
invent a
the
system with two springs.
what I also learned by discussing with them is that they don't have always the same operator, which may change things. Sometimes, I mean, since 20 years they're working in there, operator who are drilling and enclosing in the cells, they're not always the same.
Yeah.
So which introduces some uncertainties in the way they handle the material. And the last time we started working with them and we had so poor reproducibility, first mechanical tests, we couldn't really understand why. And then we started checking systematically and we found that maybe 50% of the cores we got from them were already pre-damaged, strongly pre-damaged. So this complicates, but finally we decided just to pre-select the samples, and then things got better. So,
but this is really a challenge working with this material.
This material is very difficult to preserve.
Yeah.
But the cells otherwise work because we opened cells 10 years after sometimes, and they didn't lose everything. I mean, some of the cells still contained about 5% to 8% instead of 7%, which is not bad 10 years after, which means that at least physico-chemically it was isolated.
Yes.
Okay.
I just have an opinion on it. So if we don't have access to drilled quarry, so if we collect materials that have clay minerals like argillites and from outcrop and perform rock deformation experiments, so how can we preserve the moisture content and other things, or should we report the values in dried state so that reproducibility is high?
You want to reproduce the samples in the lab?
No, not reproduce the results. The results can be reproduced. So if we take from the same outcrop, if we take again and perform the mechanical test, the results are similar.
Taking samples from outcrops, I will do like for limestone, for sandstones, for like more resistant rocks, but for a clay rock, I think that will be quite different. Because this is submitted to every atmospheric condition. I don't know if it can exist in a good condition. That I think that will be potentially very different from the rock. Because this is the practice in most petroleum engineering projects. You take samples from outcrop because it's much cheaper.
And
more or less the same thing.
Access to the core sample
because in this particular case we have access to core samples because there is an underground laboratory.
Okay.
So we have quite easy access to the samples. But I cannot imagine to do this from the outcrops. I will not be confident. I will not buy the whole Orange laboratory in this case because that will be quite different.
And besides, the ATA is interested only in the samples that are coming from the lab, from the underground lab.
Yeah.
Exactly the same depth and so on. At some point I proposed them to synthesize samples as experimentalists. Well, of course, they laughed. They said, okay, what could you do in the lab? This has been done already in the earth millions ago, and this is exactly what we want.
Yeah. Because everything is in the history of the sample, so it is all the history of the history of the sample that makes it behave its behavior. So I think what we have made in making laboratory, I think we will not have the same behavior.
Well, from all the type of materials probably, but not the clays. Okay. Well, so we are at the end of this summer school. Maybe we should thank again the